Well, all right, guys, I think I'm going to go ahead and get started. It's about 7 o'clock. It's great to see all of you. Thank you for coming. I'm glad you're here. I hope that if you've had some finals already, that you're feeling in the rhythm of it and that hopefully it's going pretty well. I know we're kind of still at the beginning of the week here. Busy times, but it will be wrapping up soon, as you know. Um, Before I get into what I'm mainly going to do tonight, which is to solve a bunch of problems with you, just gonna get my schedule out to you. We don't have very much of a schedule at this point. I'm going to do this session. I'm really committed to stopping before 10. The session that I did yesterday went for 3 hours. I do not really want this to go any longer than that because by 10 o'clock, everybody needs to be like getting their own studying done and get some rest, if nothing else. I'm going to go for an absolute maximum of 3 hours. Maybe it'll even be a little less than that if I talk a little bit more efficiently than I did yesterday. After the review session, I am going to go down to my office. I may not be pulling an all-nighter, but it's certainly going to keep me here till at least midnight tonight. I will be here late because I also have another class that has a exam tomorrow, and they may have some questions for me later tonight too. They're all right outside my office right now as we speak, studying, and they'll have some questions, I'm guessing, by 10 o'clock. So I'll go downstairs. You're welcome to follow me down there if you want to stay on campus. You can also go over to the library, which is open all night. And at some point, I will go home, I think, and I will be back early tomorrow. Our final for the morning people, the final starts at 9. So I would like to be over to my office at least by 8, hopefully a little earlier than that. So if you have a last minute question in the morning, of course, that would be fine. Just don't come in tomorrow at 8 expecting me to do like a massive review of a whole bunch of stuff. That probably won't happen. But anyway, the morning final starts at 9. And remember, I'm going to give you some extra time. So technically, you should count on having till at least 11:30 to take it. And then I'm going to I'll take a short break. I'll come right back up here again at 1 o'clock, and I'm going to go for the afternoon session from 1 o'clock until 3:30-ish, that kind of thing. And you can choose when you want to take it, depending on your schedule. Some of you may not have a choice, but doesn't matter whether you're in my morning class or my afternoon class. You can come either at 9 or at 1 and take this final at whatever time you would prefer. So it's just your call. As far as that goes, I won't be around to help much. If you're thinking, well, I'll wait till 1 so I can ask a bunch of questions. Unfortunately, I'm going to be stuck in here proctoring for most of that time. So it'll just be if you want to use some extra time to do your own studying, that'll be possible. Okay, so that's my schedule. I would definitely recommend that if you haven't tried at least one of the sample finals that's in my Canvas page by now, I would recommend prioritizing that. If nothing else, you go to this review session, you go home and get some sleep, and then you wake up and try my sample final. That would be a reasonable thing to do if you haven't done that yet. There's actually 2 sample finals. So some of you maybe have tried one and want to try the other one. That's also fine. But just don't burn yourself out completely on this. I mean, you guys know yourself better than I do as to how well you could pull an all-nighter, but I really would feel much better if people are getting a little bit of rest between now and tomorrow. That would probably be a good thing. Let's see, what else did I want to say? There's other things in the resources folder as well, but if you've looked at both of the sample finals, yeah, you could go back and look at the group work again, perhaps. But for the most part, those sample finals, I think, are going to be really a good thing to look at. Between the 2 of them, it has a lot of good coverage. And actually, as I was preparing for this review session, I looked at the questions in the review session list. That there's a document for that online. And then I also pulled up yet a third I have like 20 old finals because I've taught this class like 20 times. So I looked at another one of my old finals and, oh, those are actually pretty good questions too. So in the review session last night, I did some of those problems instead of going off of the review session questions, I went to a third sample final that you guys have never seen before, and I just used those problems. And I'm going to do that again tonight. I'm going to use some of the questions off of the review session, but I'm also going to take some questions that are off of one of my old exams. I just think that these old finals are very well lined up with kind of the way I've been teaching the class the last few semesters and kind of what you should expect that I'm going to give you tomorrow. So that's why I've been doing that. And that's why I've been telling you that if you could only do one thing to get ready for our tests, I would recommend that it would be to go over the sample finals. So that's kind of my suggestion on that. Okay. Does anybody have any questions for me about any of this stuff? I have written the test already. It's very unusual that I do that, but I do have it written. There will be 130 points that you can get, but I'm only going to be grading it out of 110. So what that means is that you can play that one of two ways. You could choose to skip a couple of things and still get 100% even after skipping, or you can just go ahead and go for everything. Why not? Go for the whole exam. I used to do it where I would say, oh, I'm only going to count your 10 best problems out of 12. And then I would ask the students to cross off 2 of them. And what often happened was the students would not cross off the ones that were in their best interest to cross off because they were crossing off problems that they would have had more points on than the ones that they left for me to grade. So I took that out. So you don't even have to think about that. You're just going to solve as much as you can, knowing that if you skip something, or even a couple of things, you're still above 100%. 20 points is going to be 2 or 3 questions worth probably. So there will be that cushion there. So keep that in mind as you're going along. Okay. Anything else that I could answer before we go any further? Okay. If not, I'm going to start off. I'm going to spend the next 2 hours and 53 minutes just doing sample problems. And you'll be amazed how fast the time goes because there's a lot of material. There definitely is. So let's do some practice, guys. So let's, this is my review session number 2. And I'll try to make a reference to where these problems are that I'm doing, that I'm going to do. I'm going to start right away with problem number 1. Sorry. I'm going to do problem number 9 from the review session handout. So I'm actually going to go straight to the review session handout for this. And that's because I like this problem. I think this will be a good one. And what it asks us to do, guys, is to solve this equation, right? Y prime minus 3 over 2x times y equals 6 times y to the 1/3 power times x squared ln of x. Okay, so there you have the first problem. Now, what I'd like to do is, you remember on our last day of class, I did a little flow chart about differential equations. You can see this is a differential equation. Let's just kind of remember the flow chart. The question that I always like to ask first is, am I looking at a single differential equation with one unknown function? Or am I looking at a system of differential equations with multiple unknown functions? What would you tell me here? Is this one differential equation with one unknown function, or is it a whole system? It's a system. So what are the unknown functions? I see y. The derivative of y is there. Is there another unknown function there? I don't think so. I don't think so. This is a single differential equation with one unknown function. Guys, if it's a system, you will see multiple unknown functions. Could be x1 prime, x2 prime, x3 prime, several different derivatives. And it might even be presented to you in a matrix. So it will look like, okay, this is a linear algebra system, and there's basically a system of unknowns to solve for. This is not like that. This is one single differential equation. So if you remember from the flow chart, if I have one single differential equation, the next question I like to ask is, what is the order of this differential equation? Can somebody tell me? Aiden? It's first order, right? The highest number of derivatives that I see here is 1, right? So this is first order. Okay, and guys, if I have a single first order differential equation, then that means that we are looking at chapter 1 of the book. So we're talking about either separable, linear, Bernoulli, or homogeneous. Those are the 4 kinds of first order differential equations that we studied. And I'm literally taking us back to the beginning of the semester here. This is from chapter 1, and I wanted to review it because we haven't probably studied this as much lately. So this is going back to chapter 1, separable, linear, Bernoulli, or homogeneous. So that's actually the next question in the flow chart is which type is it? Does anybody have a thought about this? Which type it is, Aiden? It is Bernoulli. It is Bernoulli. Now, let me just remind you all about the way these equations look. If the differential equation is linear, it will look like the following. For a linear differential equation, you would have y prime plus p of x times y equals q of x like that. Okay, and the difference between a linear equation and a Bernoulli equation is that for a Bernoulli equation, it's going to look like y prime plus p of x times y equals, and then on the right side, it's going to be q of x times y to the n power. And so the only real difference here is whether there's a power of y on the right side of the equation. And I can see that here directly. And in fact, so this is a Bernoulli equation with an n value of 1/3, right? So the n would be a 1/3 on this one, okay? But other than that, this is totally in the form of a Bernoulli equation. And so the p of x is just the part that's over here in front of the y. Be sure to include this negative on it though, guys. So it's negative 3/2x. And then the q of x is everything on the right-hand side except for the y to the n. So in this case, that would be 6x squared ln of x. That would be the q of x. It would be all of the stuff other than the y cubed. So you'd grab all of that and you'd have your q of x. So does that make sense to everyone? Now, we have to remember how to solve a Bernoulli equation. First of all, let's say you don't remember tomorrow. You suddenly forget. But you know that it's Bernoulli and you can tell me what n is. And maybe you can even write down this form of a Bernoulli equation. You should do all of that because I'm going to give you credit for all of that. A lot of times people will just punt on a problem completely and then I can't give them any points. When in fact, if you know that this is Bernoulli with n equals 1/3, you're likely to get 20 or 30% of the credit just for identifying the equation and at least telling me the form and the n value. So just do it. Just put down as much as you know, okay? What you'll have to do in order to actually solve the equation is a change of variables. So if I could remind you, the Bernoulli equations always get converted into linear equations through a change of variables. And I'm going to write it here for you guys. It's u equals y to the 1 minus n. So right now on this first problem tonight, I'm trying to do something where there's a fair bit of equations to learn. Okay, so if you have forgotten some of these equations, I'm trying to get them back into your head again. So you'll need to know this if you really want to be able to solve the equation. So in a minute, I'll plug in the n value here, and this is the change of variables we have to know. The other thing that's really important to know, technically you could derive it if you had to in the spur of the moment on the test, but you don't want to have to do that. Better to just know what is this new linear equation that you end up with. So this one is equally important to know, and I'm just going to write it here, guys. It's going to look like u prime plus 1 minus n times p of x times u equals 1 minus n times q of x. Let's put that in a box as well. That's really important as well. And the thing about this is to just remember that you're putting a 1 minus n in front of both the p of x and the q of x. That's the main thing that happens. The other thing that happens is you lose the power of the unknown function on the right side. So on the right side here, I only have the X stuff with a number in front of it, and everything else is kind of vanished. Okay, so this is worth memorizing. And again, don't think of it as, oh gosh, I've got such an overwhelming thing here. It's more like, okay, there's a couple more points I can get. There's a couple more points I can get. Everything is worth points on a problem like this. By the way, you should definitely expect one of these tomorrow. How come? Well, if you look at my sample finals, you'll see I always seem to have one of these. And there's a reason for that. And it's because this single problem right here reviews half of chapter 1. Because not only are we reviewing what the Bernoulli equations look like and the change of variables technique, but then you also have to then solve this equation, which is linear. So this one always becomes linear once you've done that change of variables, okay? So I pretty much am promising you that if you put a little bit of time into learning these equations, you're going to help yourself out a lot on the test, okay? So that's the setup of it. So actually, so for this problem, let's figure out what these expressions would be. So we have u equals y to the 1 minus n, but I already said that n is 1/3. So this just becomes u equals y to the 2/3 power. All right. And then what does my new differential equation become? Well, it's going to be u prime plus 1 minus n. N is 1/3, so 1 minus 1/3 is 2/3 of p of x. The p of x is up there on the top of the board, guys, -3/2x. That's multiplied by u. And then equals, the right-hand side of the equation also has a 1 minus n, which would be 2/3, multiplied by the same q of x that we already identified, which is 6x squared ln of x, just like so. Okay, and I would probably take just a moment and simplify this before we go any further. I can see that there's a 2/3 and a 3/2 that will cancel. I'll just end up with a minus 1/x times u here. And then on the right-hand side, if I take 2/3 of 6, I'm just going to have 4, right? So 4x squared ln of x. So this becomes my linear differential equation. We're definitely at least halfway done with the problem now. Does anyone remember the method for solving a linear equation? Levi?
Oh, you integrate for y on both sides.
I'm sorry?
You integrate for y on both sides.
Integrate on both sides. At some point, we will be integrating on both sides, but there's a word for a thing I'm looking for here. Yes?
Separation value.
No. Right? Integrating factors is what it is. Are you enrolled in my class? Okay, you're welcome to be here. That's fine. I just wondering. Huh?
Oh yeah, Andrew, that's
fine. Okay, yeah, no, I'm glad you're here. It's no problem. Okay, so integrating factor, does anybody remember the integrating factor equation? I was just gonna be embarrassed if I wasn't sure. I was like trying to remember, who is this guy? I was like, did I forget? Did I forget about some of my students? I hope not. Anyway, the integrating factor, does anybody remember the formula for it? Is that?
I equals e to the integral of dx dx.
That's it. And again, guys, even if you don't actually know how to solve the problem, if you just write that down, I will have a smile on my face. I will like that, okay? The one little caveat with this is the p of x that you see here is not the original p of x at the start of the problem. It's the new p of x that goes with this linear equation, right? So if I look at this linear equation, my p of x is the part in front of the u here. Let's go ahead and put it in there. And I also want to really urge you to be careful. This is a minus, and that minus is part of this p of x. So it's e to the negative integral of 1/x dx. That's really important to keep that minus sign. Guys, something as simple as a lost minus sign will throw everything off. You'll end up with something to integrate later that is so much harder than what I ever intended it to be, right? So it's really important to be careful. Like I wouldn't take, like if you made a sign error, I wouldn't take off a lot of points for the sign error, but what would happen is you would struggle to finish the problem. Because the wrong integrating factor is gonna make the rest of the solution not what I meant for you to be doing. So that's why it's almost more important to get that right for the sake of being able to finish the problem than because I would take off a lot of points. I definitely would not. But I do want you to be able to finish the problem. This should be integrated. This is gonna be e to the negative ln of x. I'll make a couple of quick comments about that. When you're doing the integrating factor here and you're solving the integral, you do not need to add a plus c on the integrating factor. That's one thing. The other comment I want to make here is that you might be wondering if I should have absolute value bars around the x here. When I integrate 1 over x is normally the ln of the absolute value of x. However, I should have said in the very beginning that this problem wouldn't even make sense for negative values of x, because even in the original question, the natural log of x shows up there, which means x is only going to be positive anyway. So I might as well just kind of take that as an assumption. If this was really on the exam, I probably would have wanted to like just over on the side, just said something like that, just so you don't get confused by that. So you don't need the absolute value bars around that. Now, I would like to cancel the e with the ln, but be careful. If there's any number kind of sandwiched in between here, I have to use properties of logarithms first. And whatever that number is can be put inside the argument of the ln function as an exponent. So the -1 goes upstairs. And now e to the ln of whatever is just whatever. Okay, in this case, 1 over x. All right, so there's my integrating factor. Okay. And what's the next step? The next step technically is to multiply your linear equation through by that integrating factor. What will happen is so let's just see what's going to happen. When I take this equation, oops, I need to give myself enough room to actually write the result here. When I take the linear equation there and I now have the integrating factor, on the right hand, I'm just going to multiply everything through by that integrating factor. So on the right hand side, I'm multiplying through by 1 over x. And technically, I'm doing it on the left side too. But when I do it on the left side, guys, what ultimately you have is actually a product rule. Basically, this is how the whole process works. You get your integrating factor times your unknown function with a derivative on it. So it becomes a derivative of that product. Yeah. Okay. So this is essentially what it is. It's another thing you have to kind of remember, that after you find the integrating factor, you will have created the derivative of the product of the integrating factor with your unknown function. And then on the right hand side of the equation, you just take whatever the q of x was, whatever this q of x was right here, and multiply it by I. Which actually, by the way, we can just cancel an x from the top and the bottom here. So we just get 4x ln x on the right side. And at this point, we are ready to solve for u by integrating both sides. So I'm going to integrate both sides. So on the left side, when I integrate, I get rid of my derivative. And on the right side, when I integrate, I have 4 times the integral of x ln of x dx. Now that integral really isn't that hard. It's done by integration by parts, but you should not be expecting me to ask you integration by parts, because there's maybe been one problem on that in the whole semester or something. It just doesn't come up enough for me to pull it out now on the final. I'm going to make these integrals something you can really do easily. In this case, you're going to do it by just looking at the table. Okay, so this is from the table, and it's number 8 on the integration table that I have been passing out, right? It's in Canvas if you need to review it. But this will be given to you. And if I just use the formula here, we can write down this integral. I'm just going to do it really fast here for you guys. It's x squared over 4 times the quantity of 2 ln of x minus 1. Now, this time, I do need a plus c. when I'm doing this integration at the last step, I have to add a plus C on the right-hand side because this is, after all, looking for a general solution. So the general antiderivative there, okay? It is perfectly okay to leave it like that, but if you wanted to simplify it, the 4 and the 1/4 could obviously be canceled. That would leave me with x squared times 2 ln of x minus 1. And then notice here, guys, 4 times c should technically be written as c1. 4 times c is, I've got 4 and I've got c, that becomes a new constant c1. If you just relabeled it as c again, I probably wouldn't get my red pen out for that, but technically it should be a C1. I do want to caution you though, so don't write this down or change your notes or anything, but if, let's just imagine that this had been an X here. I'm sorry, let's leave this as a C. Sorry, let's imagine that this had been an X right here. And then I multiplied it through, so if I multiplied it through, this would become x cubed over 4. And then this would be just c times x. I have seen students make the mistake of changing that to c1. Now see, if there's an x in the expression, it's no longer a constant. And so c times x should not be relabeled as c1. C times 4 can be relabeled as C1 because that's still just another constant. But if there's an X in this expression, you should just leave it as C times X if that's what it is. No need to simplify that. In this case, what we really had here though was a 4, which means when we multiplied it through, we got an X squared, and here we got a 4C, which I'm just calling C1. This is a completely optional step. If you're like worried that you're going to mess up the simplification of it, then don't simplify it. You don't have to, okay? I'm not gonna make you do that. All right, the last thing then is to solve for u. To solve for u, I need to divide by I, right? So I have to divide by I. So I take my whole u here, just recopy it. And I'm going to divide by the integrating factor. The integrating factor was actually 1 over x. Okay. And when I do that, come over to this next board. Actually, what is going to happen now is I'm going to multiply it through by x upstairs. So it's going to become x cubed times the quantity of 2 ln x minus 1 plus c1 times x. And this time I'm not going to change that C1x into another constant. So am I done here? Why not, Oscar?
We gotta put it back in terms of y, right?
Exactly. The original problem was in terms of y. So this is what u equals, but I need to know what y equals. And that's why writing this down, and I like to do it at the beginning of my solution, writing down that u is equal to y to the 2/3 is helpful. So let me just add that here, guys. So u is equal to y to the 2/3 power. So if I wanted to solve for y right now, what I would do is raise 3/2 power on both sides. 3/2 power on both sides. So the y becomes, it's this whole thing to the 3/2 power. So let's just write it down for the sake of getting to the answer here. It's gonna look like that. Yeah. So that's your general solution. That's your general solution. Now, if I give you an initial value, somebody was commenting that they saw a lot of initial value problems in the sample of finals. Then if that's the case, by the way, that's only like 10% of the whole problem, so don't freak out about it. But that's just where you plug in the initial value for x and the value for y and solve for c, in this case C1. So you can solve for that constant to get a particular solution in that case. So this is the general solution. It's a whole infinite family of solutions, right? Indexed by this C1, which could be any number. But if I specify an initial value, that will in turn force us to specify a value for C1. It'll get pinned down by that initial condition. Okay, so I won't dwell on that part of it for right now, but this is This is the general solution. What do you guys think? Are there questions about this one?
Wait, can you see it for the 2/3? You got it from the original?
Yeah, the u
Oh.
equals y to the 1 minus n. So just from here, yeah, exactly. So I have to use the 3/2 power to get rid of the 2/3 power. Yeah, that's right. Good question. Anything else for the moment on that one? There's a lot to this. But if you know how to do a Bernoulli equation, that means you know a lot of the stuff from chapter 1. Because it involves a lot of parts. You have to know the linear stuff as well to fully go all the way through the problem. So definitely be on the lookout for something like that. Okay. So far, so good. Sweet. Okay, let's move to another problem. I'm gonna jump around, by the way, as well. I'm not gonna just go in a straight line through the material. I'm gonna kind of jump to different things. So let's go to number 1 from the review session. I just did number 9. Now I'm gonna go back to number 1. And I'd like to have us try to solve this setup here. X prime equals negative x plus 2y plus 54t e to the 3t. And then y prime equals negative 2x plus 4y plus 9 e to the 3t. So I see derivatives here. This must be differential equations. Let's think about the flow chart. First question, is it a single differential equation with one unknown function? Or is this a system of differential equations with more than one unknown function? It's a system, yeah. By the way, that question, is it a system or not? It's really not supposed to be a hard question. You're supposed to be able to just look at it. Is there more than one unknown function here or not? You can definitely see that, right? X and y are both functions because I'm taking derivatives of both of them, right? So this is absolutely a system of differential equations. So then if you remember from the flow chart, and again, I don't have the flow chart with me, but it's certainly in my lecture from last Thursday. The next question was, is it a homogeneous linear system? So it's a system of differential equations. Is this homogeneous? And I'll just remind you that homogeneous means that the system could be written like this, right? Whereas, so this would be homogeneous, but whereas non-homogeneous, which would be the other choice, a non-homogeneous system would be expressible this way. And I'm going to write down the matrix and the so on in a minute, but I just want to make sure we're understanding. Does this look more like the homogeneous or the non-homogeneous setup here? One more time. Yeah, non-homogeneous, right? It's non-homogeneous. The thing about the non-homogeneous system is that there's stuff appearing here that is unattached to x1 or x2. It's unattached to, x or y. It's unattached to my unknown functions, which in this setup I've used x and y. So yeah, this is absolutely a non-homogeneous system of differential equations. How do we solve those? That's exactly what we learned on Thursday. So this is from section 9.6. You guys had to do 2 homework problems on that. By the way, my grader finished grading all of the homeworks for the whole semester just this afternoon. So at this point, that's all a done deal. I have to go through and drop your 2 lowest ones and do all that stuff later, but you should have all the solutions to all the homeworks, and we're all good to go on that. But this last homework had just 2 problems on it, and now we're going to practice another one just to make sure everybody's good on this, okay? So this would be expressible, guys, as x prime equals, and then I'm going to make a matrix here. This matrix is what I'm going to call A, and then we're going to have a vector here on the end, which we're going to call B. So it's going to look like this setup right here. Okay, so the matrix A has just these coefficients on it. And the first row just goes straight across the first row. So -1 and 2, and the second row goes across the second row. Try not to get confused and try to transpose it. Okay, just go lay those numbers in there just horizontally across the rows. So the first row is coming from the first equation, the second row is coming from the second equation. Right, okay? And then the B vector is just the part that's tacked on to the end here, guys. So 54t e to the 3t, and then on the bottom slot, 9e to the 3t. So there's your B vector. And now we just need to solve this system. And I think I'm going to need a fair bit more room. These first two problems that we're doing tonight, actually, both of them take a little bit of effort and time. So thank you for your patience with me. But the good news is we're covering a lot of ground by doing these two problems. So let's give ourselves some more room here to do that. So remember what we learned on Thursday? It's just a 3-step process. Step 1, find the complementary function. Step 2, find one particular solution. Step 3, add them together. Okay? And to whatever extent you can do as much of that as possible, I'm giving you points for every part of that process. This kind of question would be worth a lot of points because it has a lot to it. And so you don't want to just punt it away without at least trying to put down the parts that you know. Even just taking this thing and putting it into the matrix is worth some amount of partial credit. Okay, so go ahead and try to do that. Step 1, though, let's get into it now. This is where we have to find the complementary function. And to do that, so this is what I denote as x sub c of t. To do this, we have to find the eigenvalues of our matrix. So I have to subtract lambda off of the main diagonal of my matrix. So -1 minus lambda and 2, and then -2, and then we have 4 minus lambda. So there's your 2 by 2 determinant. And let's just do our AD minus BC formula on this one. So this becomes -1 minus lambda times the quantity of 4 minus lambda, and then there'll be a +4 on the end of that. Because it's only going to be a quadratic equation, I don't mind just multiplying it all the way out. I'll have a lambda squared, and then I have a plus lambda and a minus 3 lambda, which is a net total of I have plus lambda and minus 4 lambda, which is a net total of -3 lambdas. And then I have a minus 4 canceling with a plus 4. So actually, this is the whole thing. This one, you can easily just factor it. If you were not able to easily factor it, you could still get the roots, of course, by just using the quadratic formula. Folks did a really good job on the recent midterm in getting these eigenvalues worked out on these problems. So I am hoping that will still be true with the next test. Factor out that lambda, and then as you know, guys, to find the lambdas, we need to set this one equal to 0. I'm going to set this one equal to 0. And you can see that your lambdas are going to be 0 and 3. I highly recommend taking 2 seconds to just check those lambdas with the fun facts. So if you go back to your matrix here, the trace of this matrix is 3. If I add up the main diagonal, I get 3. So you can see that when you add up those lambdas, you get 3. And the determinant of this matrix is -4 plus 4. That adds up to 0. By the way, this is really not an important point for this problem, but this matrix A is not invertible, as it turns out. If you just look at this matrix, the second row is a multiple of the first row. When you do the determinant, you get 0. So it's not an invertible matrix. That doesn't really affect the solving the system of equations, which is what we're doing here. So, it is just a side observation that by getting one of those lambdas to be 0, that pretty much tells you that your matrix is not invertible. Okay, and also the matrix is not defective either. It's not defective because you have no repeated eigenvalues. Remember, if this eigenvalue did not pull its weight, then you'd have to do that picture with the W's or whatever, something like this that we learned last week as well. So that actually we learned the week before last week, I guess. That's something that could come up. But in this case, you don't have to worry about that. You also don't have any imaginary numbers. If there were imaginary values for these lambdas, you'd have to do the Floyd process that we learned a couple of weeks ago as well. So there's a lot of things that could happen here, but in this case, we got two distinct, nice real numbers out of it. So that makes it easy to go on and find the corresponding eigenvectors directly. So I'm just going to find my lambdas now. So starting from lambda equals 0, I need to do a null space, right? So I'm going to do a null space. And it's a null space of what? It's the null space of the matrix that I get when I subtract lambda from the main diagonal of A. Well, lambda is 0 here, so I'm not really doing anything to A, right? It's just A itself. So it's just -1 and 2 and -2 and 4. That's your matrix. And these two rows are always going to have to be multiples of each other. I'll go ahead and just cross one of them off. Okay. And then I'm just going to use my little A-B trick on the first row here. Hopefully by now you know what I'm talking about. This just means I'm going to swap the order of the two values and do a sign change on one of them. So I think I'll just do a 2 and a 1. Okay. So you take, this is your A, this is your B, and to make your vector, you just create B negative A. All right. And then from there, we can go ahead and write down our first solution to the system, which is going to be x1 of t equals e to the 0 times v. Well, actually, e to the 0 is just 1, so it's just v itself. So that's my first solution. Slow me down if I'm going too fast. It's a long process. So a lot of this is pretty easy on a 2x2 matrix though. So I can do step 1 relatively quickly. Let's do the other eigenvalue here, guys. When lambda is equal to 3, I'm going to take the determinant of the matrix I get when I subtract 3 from this main diagonal. So when I do this, by the way, for those of you who were here last night, I did not do this problem last night. I did a similar one. I'm just trying to give a different example. So if I subtract 3 from the main diagonal, I'll have -4 and 2, and then I'll have -2 and 1. Right. The two rows are multiples of each other, as they must be. I'll cross one of them off. Then I'll do my little A-B trick on the row that I'm keeping, and that allows me to write down my vector, which is 1 and 2. And then I can write down my second solution. So x2 of t is e to the 3t times the vector 1 and 2. Okay. So far we got all of that. All right. At this point, we're really done with step 1. I just want to write down the complementary function though, so that we can summarize everything that we've put together here. So we'll just come over here and write down the complementary function. This is x of c of t is going to be c1 times x1, which is 2 and 1, plus c2 e to the 3t times x2, which is 1 and 2. Just like that. Yeah. I'd recommend putting a box around that one so that you can find it later if you're going to need that, which we are going to need that. So we can highlight that as an important step. Okay, so that's the end of step 1. It's 3 steps, guys. Step 3 is easy. We just did step 1. The main thing that we have left to do here is the step 2 part. Are there questions so far? Everybody with me? This isn't conceptually that difficult. What makes this a little bit of a heavy lift is just that there's a lot of steps. You got to kind of not lose track of where you are on the roadmap of everything that goes into solving one of these. But just be patient with yourself. like I said, there's a lot of partial credit to be earned every step of the way along here. For step 2, we have to find one particular solution. So let me remind you, this is an equation that we just learned last week, so it's important, which is that we're going to take the particular solution to be the fundamental matrix X times U. And the fundamental matrix is the matrix that we can build. It's the matrix that we can build by putting the x1 and the x2 into the columns of this matrix. So the first solution was just 2 and 1. So I'm just going to lay that into the first column. Okay. The second solution is a 1 and a 2, but with e to the 3t in front of it. So I'm going to shove, you remember I did this last week, I shoved the e to the 3t into the slots of that vector. So this becomes e to the 3t and 2 e to the 3t. You're going to want to have that there. That's my fundamental matrix. Okay, so far so good. I need a bit more room yet though. Get this cleared off here. Okay. When you're figuring out what U is, you have to remember what the formula for it is. So I'm just going to remind you about that. The U formula is calculated by doing an integral of the inverse of the fundamental matrix times B. So these two equations are the new equations from this very last section that we learned that you will want to make sure you know. Okay? And I know our test is coming right up, but it's never too late to make a flashcard or two and just quiz yourself a few times on it and get this down, okay? So the U vector is the integral of the inverse of x times b. This is x. By the way, it will always be invertible, so don't even have to worry about that. The x inverse will always exist. And how do we find the inverse of this? Well, you have to remember, maybe I'll squeeze it over here so it's not in the way of my main work. But this is a nice formula that we learned way back in chapter 2. Just how do you take the inverse of a 2 by 2 matrix? It's just coming, you can just write down a formula for it. So I'll just remind you what it was. We take the determinant of the matrix and put it in the denominator. And then I'm going to swap the two diagonal values. And I'm going to do minus signs on the other two values. So this is the formula. It's worth knowing that just to save some time, right? Just to save a little bit of time. So with that understanding, let's see if we can write down the fundamental matrix inverse here in this case. Okay. So it's going to be 1 over, and then it says AD minus BC. Well, AD is 4 e to the 3t. And then BC is e to the 3t. So 4 e to the 3t minus e to the 3t is actually just 3 factors of e to the 3t. Okay? And then I'm going to swap the diagonals. So the upper left corner will now be 2 e to the 3t. The lower right corner will be a 2. And then I'm going to do sign changes on the off diagonals. So the 1 becomes a -1, and the e to the 3t becomes a negative e to the 3t. So it's going to be something like that. That's my x inverse. Okay. If you want to shove this scalar into the 4 slots of the matrix, you certainly can do that, but it's not necessary to do it. And I don't necessarily recommend it because it's kind of nice to keep this fraction outside rather than cluttering up the interior of the matrix. Just leave it like this, okay? Once I've got x inverse figured out, I'm going to multiply it by b. Okay, so let's come up here to do that. X inverse times b. This is 1 over 3e to the 3t. And then we have 2e to the 3t, negative e to the 3t, -1, and 2. And now I have to multiply that. I'm going to need to erase this already, I'm afraid. I now need to multiply that by the b vector. We haven't even touched this b vector yet. which is over here. So I have to take that B vector and stick it right here. 54t e to the 3t. And then on the bottom slot, I have 9 e to the 3t. So the B vector is given in the question, and I'm just going to multiply that against the x inverse. X inverse multiplied by B. I would not bother to do anything with this coefficient yet. I would just start doing this. This is a matrix multiplication here. I just have to go across the rows of that 2 by 2 matrix and dot them with this column to get my simplified answer. So this is going to be 1 over 3 e to the 3t. And let's see if we can work this out. If I go to the top slot of this result, I'm going to be dotting this guy and this guy, right? So, well, let's see. 2 e to the 3t times 54 t e to the 3t. 54 times 2 is 108. And then there was a t. And I have e to the 3t times e to the 3t, which becomes e to the 6t. Okay? And then minus 9 e to the 6t. Okay. On the second row, I also have to dot the second row with this vector negative of the first slot. So negative 54t e to the 3t. And then plus 18 e to the 3t. The reason I'm doing all of this right now is because I'm getting ready to do an integral, and I would like to get it cleaned up as much as I can before I actually have to do the integral. Okay. Now would be a good time to shove this coefficient into the various terms of the vector, right? Actually, every one of these numbers in front is actually a multiple of 3. So when you put the 1/3 in there, it actually does you a favor and just cuts those numbers down. The other thing is you're going to divide by e to the 3t, which is going to cut down the exponentials a little bit also. So it's actually going to work in our favor to simplify this. So the only one, let's see if I can do this in my head. 108 divided by 3, I believe, is 36. And then there's still a t, and then there's e to the 6t divided by e to the 3t. And that just gives me e to the 3t. And then minus 9 over 3 is 3. E to the 6t over e to the 3t is e to the 3t. So there we go. That's the top slot. Now let's look on the downstairs part of the vector. The e to the 3t is going to divide into the e to the 3t, which is going to completely go away. 54 divided by 3 is 18. So this becomes negative 18t. And then plus, in the last term, I have 18 divided by 3, which is 6. And then the exponentials again cancel out. That's what you have for x inverse times b. Okay. So far, so good? All right, sweet. Now I have to integrate all that. So the next step is to integrate it. If you've made it this far, you've probably gotten 3/4 of the credit of this problem, right? So we're most of the way through it. We've done all of step 1. We're just trying to figure out what the particular solution is. And to do that, I have to know what u is. So u is the integral of this. So u is the integral of this vector. So 36t e to the 3t minus 3e to the 3t, and then negative 18t plus 6. And we're integrating this with respect to t here. This is the integral that we are going to need to work out right here. Now, I've sort of done a bad thing here, guys, which is I've made an example that's probably, I wouldn't put this on your test because to actually do the integral of t e to the 3t, let me just come over here on the side for a moment, just to focus on this one part of the integration. When I want to integrate t e to the 3t, you actually have to do that one by parts. So I made a question that when I'm doing my review session, I don't worry about it as much, but you can be sure I wouldn't put this kind of an integral, although it's not that bad. I wouldn't put it on your exam, so don't sweat it. Don't sweat this. The main thing is to just know what am I supposed to do here, which is you need to integrate this vector, right? So for those of you who do like to remember how integration by parts works, I can just tell you that you would set it up this way. U is equal to t and dv is equal to e to the 3t. I have to integrate e to the 3t, which gives me 1/3 of e to the 3t, and I have to differentiate t, which just gives me dt. And then the way this integral works out, again, no need to take a lot of notes here, guys. You can just kind of follow along for a second, and then I'm just going to put the answer over there in a minute anyway. U times v minus the integral of v times du, which is the same as dt. I'm going to get something like that. And this thing, just need a little more room here. This becomes 1/3 of t e to the 3t. And when you integrate e to the 3t with a 1/3 in front of it, you actually end up with a 1/9 in front of that. So this is actually what you have. One thing about the integration you're doing right now is you do not need to add a plus c here because we're just looking for one particular solution. So we don't need the plus c, but let's just see if we can start working it out. I need to multiply this by 36. The thing I got there, I need to multiply by 36 because I really have a 36 in front of this. If I throw a 36 through this whole thing, it's going to turn it into what? 12t e to the 3t minus 4 e to the 3t. And then don't forget, you still have to integrate 3 e to the 3t, which gives you e to the 3t. Okay. I'll clean that up in just a minute. On the bottom line, I have a much easier time. The bottom line is more like, it's more like what I'll probably ask you to do, which is the integral of -18 plus 6 is just -9t squared plus 6t. Again, you don't need a plus c. You don't need a plus c. So there is your u vector. This can be slightly cleaned up in the upstairs portion if I actually just factor the e to the 3t out of it. I'll have a 12t minus 5, right? And then other than that, I wouldn't bother to clean anything else up. I would just leave it as is. That's u. And so the last thing I need to do is write down my particular solution, which is capital X times u. This is going to be the end of step 2, is to write that down. I'm going to go ahead and erase my integration by parts. So the particular solution, my friends, is just capital X times u. And we should have all of that stuff ready to go now. Capital X is just 2 and e to the 3t, and then 1, and then 2e to the 3t. And I'm going to multiply that by this vector that I just wrote down, which was e to the 3t times the quantity of 12t minus 5. And then -9t squared plus 6t. And I just have to work this out. So I'm going to do one more matrix multiplication here. So going across the first row and dotting it with that column, let's see, I'll get 2e to the 3t times the quantity of 12t minus 5. Plus e to the 3t times -9t squared plus 6t. Right, and then on the bottom slot, I'll have e to the 3t times 12t minus 5 plus 2e to the 3t times the quantity of -9t squared plus 6t. That's a little messy looking, but it's just 2 slots. It looks like it's a wide, fat matrix, but it's actually a very skinny thing. It's just a vector. I would not spend my time to clean that up. I would just leave it like that and be good with it. Okay. And then step 3. Step 3 is where you can earn some really easy points, guys, by just remembering to write it down. All you're doing on step 3 is you don't need to recopy all of the stuff you've already worked out. You can just put the summary here, which is the complementary function plus the particular solution gives you the final answer. So step 3 becomes really easy. Okay. Questions on this? The integral was a little messier here than I wanted it to be, but aside from that, not too bad. You will not have a problem tomorrow where you have to do integration by parts. Some people may choose to, but you shouldn't not have to. Having said that, there will be a question on the test that is about this topic. I'm pretty much promising it right now. So just be ready for it. Questions there? And it'll be worth a lot of points because there's a lot of steps involved here. So it's definitely one you want to make sure you're comfortable with. Yes. Mhm.
Why did it doesn't matter?
It doesn't matter which row you cross off here. If you did EROs on this matrix, one of those rows would get zeroed out. So you can take your pick which one you want to zero. I usually try to zero out the one that has the messier looking numbers in it, but it can be whichever one you want. Yeah. Okay. Other questions on this one, guys? Okay. If not, I'd like to go to another problem. Yeah, let's do this one. This one is off of an old final from the past that I don't think I've shared with you guys. So let me just put it here. This will be interesting to see. This takes us back a little ways. Let's compute. Let's switch gears again on you. A 2-1 entry of A inverse, where capital A is the following matrix. It's going to be a 4x4 matrix. The first row is -2, 0, 1, and 4. And then on the second row, -1 and 1 and 3 and -1. And the third row is 3 and 2 and 0 and 1. And the fourth row is -1 and 0 and -2 and -2. So this one is not in the resources anywhere, guys. I'm basically pulling this one out of the sky on you. Okay. So sort of a new problem. I did not go over this last night. I thought that this might be a nice one for us to try right now. Okay. Yes. My papers are all over the place. To get myself a little bit better organized here. The trick with this one is we're not being asked to find the entire A inverse, just one of its entries. So you might remember that there's 2 techniques for doing the inverse of a matrix. There was in chapter 2, there was something that we called the Gauss-Jordan method. So this is reviewing from way back in, I guess, February or so. The Gauss-Jordan method, this is the one where, you know, you start with your matrix, you augment it with the identity matrix, and then you just hit this thing with EROs, and eventually you try to get the identity matrix to show up on the left half of this block. And if you're successful, the inverse of your matrix actually will be, in that moment, will be showing up on the other side of that bar. So this was one method that we learned for finding the inverse of any matrix. But the problem is that it involves a lot of EROs, and you really have to go beyond just row echelon form. You actually have to make the left side completely all the way to the identity matrix. That can be a lot of steps. And if I ask you for the whole A inverse, that might be a reasonable thing to do. But they're only asking us for 1/16 of the entries of the A inverse matrix here. They're not asking for very much. So it seems like it's a lot of extra work to find the whole A inverse matrix when I ask a question like this. So when you see a question that's trying to pick off a specific entry of the inverse matrix, then we want to think maybe about another method, which was in the very next chapter, which is the so-called adjoint formula for A inverse. So I'll write it down here for you guys. What it looks like is 1 over the determinant of A multiplied by what we call the adjoint of A. So this is multiplied by the adjoint of A. And just to take it one step further, the adjoint of A is simply the transpose of the matrix of cofactors. Let me just write it like that. It's the transpose of the matrix of cofactors. And the thing about the matrix of cofactors is you can pick those off by targeting in on a particular cofactor, right? So this chapter 3 formula is well set up for picking off a specific entry that you're looking for, right? So you are really looking for the 2-1 entry of the transpose of the matrix of cofactors, which is, in other words, that is to say, so here we want the 2-1 entry of A inverse, and what would it be? Well, every entry has a determinant of A downstairs. And then what's upstairs? What's upstairs is going to be one of my cofactors, because this is the entire matrix of cofactors. And but it's been transposed here. So if I'm remembering how the IJ entry notation works, when you transpose the matrix, you swap them, right? The IJ entry of a transpose is actually the JI entry of A. So what you need here, my friends, is you need in the numerator, you need one of your cofactors, but which one is it? Not the 2-1 cofactor, but rather the 1-2 cofactor. So you have to swap those subscripts there. And the other thing I want to mention is that the cofactors really can be thought of as the minors of the matrix with some sign changes. You guys remember all that stuff? Oh my gosh. Is it back to the chapter 3? There's this thing where we do like, plus minus all the way through the whole matrix, yeah? So for a 4x4, it would look like that. If I'm looking at the 1-2 position for the 1-2 cofactor, I see a negative there. That means that actually this needs to be the negative of the 1-2 minor. Yeah, it's got to be the negative of the 1-2 minor. So what we need to do for this problem, I'm going to recommend the chapter 3 approach, not the chapter 2 approach, because I don't want to deal with a bunch of really messy EROs. I would much rather just work on finding these cofactors. And we really have 2 things to do here. We have to find the determinant of the whole matrix, and then we have to find this one particular minor. Okay? So let me give myself some room to do that. Is everybody with me so far, guys? Just ringing any bells? I know this was February. It's been a long time. It was on our first exam. Back to the first midterm. Yeah, Oscar?
Wait, so we're going from the 1-2 cofactor, right? And then we want the minor of the.
We want the 1-2 minor.
Okay, what was the minor?
The minor is just the determinant. We're going to get into that. It's the determinant of the submatrix that we get when we cross off row 1 and column 2. Yeah. So I'll do that in a second. Yeah. I have 2 things to do here. I have to find the determinant of the entire matrix, and I also have to find this one particular minor. So I'm going to do both of those things, and then we literally just plug them into that, and we have our answer. Okay. So let's just start. I usually like to just do the big determinant first. Just kind of get that over with. For the determinant of A itself, we do not have despite what some people tried to do, I think last week, we do not have a arrow method for a 4x4 matrix. The only way to do this determinant is to do cofactor expansion, or if you really want to complicate things, you can do EROs on this matrix and then try to get more zeros into it. But honestly, if you're doing that, you might as well have just done the chapter 2 approach in the first place. Let's try not to do any EROs. So if I am basically going to force myself to do cofactor expansion here, can somebody suggest a good choice for a row or a column to do this cofactor expansion on? Aiden.
The second column.
That's right. The second column has 2 zeros in it. That's more zeros than any other row or column. So I would totally choose that. It's a good idea to write that down on your paper as well so that you can justify your work a little more easily. So I'm going to expand on the second column. Okay. And if I look at my second column, I do have to be careful. I have a minus and then a plus and then a minus and then a plus. So my plus minus pattern has to be paid attention to. The first entry is a 0, but I'm actually going to write it as -0, just to reinforce to myself that that term has a minus. Then I go to a plus, the determinant of, now what is this determinant going to be right here? I cross off this row and column. Do it lightly with a pencil, guys. Don't do it real thick because you need to see clearly what you're looking at. What the numbers are that are left after I cross off that row and column is these numbers here. Right? So you just have that 3x3 matrix left after you've removed those columns. Okay. And then let's keep going. Before I actually do that determinant, I'm going to finish writing out this expansion of the second column. So the next thing I'm going to do is I'm going to write down -2 times the determinant of, and the -2 is coming from this 2 together with the negative that's in that position. So it's -2. Now I have to cross off the third row and column, and I need to uncross the second row here, guys. Yeah, so this is why it gets a little messy if you're not careful. So I've crossed off, hopefully, column 2 and row 3, and let's write down the matrix here, -2, 1, and 4, and then -1, 3, and -1, and then the bottom row is still -1, -2, and -2. We would have that, and that's going down the second column, and then the last entry is a 0. Technically, it has a plus. I'll just keep myself from getting confused by putting a +0 there. So that's the last one. So far, so good. Now you just have to do these 3x3 determinants that we have here. And of course, now you have an arrow method that you could use, right? And I probably would use it, to be honest. There's no zeros in these matrices now. It's not nice enough to do cofactor expansion. I would just use the arrow method. Does anybody want me to actually do it? Maybe I can just, you guys can handle this, right? The arrow method for a 3x3. Okay, so this gives you some number. Okay, and then we also have to find the 1, 2 minor. So the M12, well, that's just going over here and crossing off row 1 and column 2 and taking the determinant of what you have there. So the determinant there would be -1, 3, and -1. And then 3, 0, 1. And then -1, -2, -2. I think I've done that right. Based on what's crossed off, that should be about right. And again, this is just a single little 3x3 determinant. So this is going to give you some number as well. Right? And so then your answer, so you use the arrow method again, your final answer would just be the negative of whatever the smiley face was divided by whatever the number was that was calculated for the determinant. I'll just leave it at that for now. Okay. It's just something like that. Okay. That good enough for now? I'm pretty sure everybody can do the arrow method pretty easily, so I don't want to we got a lot to cover. I figure I don't need to spend too much time on that. Good enough? Okay, great. Let's go on to another topic. Here. I want to talk a little bit about inner product spaces because we didn't cover that very recently. And this is definitely something that is likely to have me asking about this. So I'm going to go to back to the review session with questions, I believe. Find the one. Yeah, I'm going to go back to the review session number 6 from the review session. And I did not do this one in yesterday's session. So I'm going to do it now. I'm going to take V to be P2 of R. And I'm going to define a formula here. I'm going to define this inner product. So I'll write it like this, guys. A naught plus A1x plus A2x squared, comma. And then for the second polynomial, I'm going to use a B naught plus B1x plus B2x squared. So I take two quadratic polynomials. These are vectors in V. And I'm going to make a formula here. And the formula I'm going to make, guys, is A naught B2 plus A1 B1 and then plus A2 B0. And I would like to ask the question, is this a valid inner product on V? So is this a valid inner product? Okay. So let me get myself some room here to work on that. So this was a topic that we talked about during the second exam. And so it's been since March, I guess, since that exam was. And we need to think about whether this is a valid inner product. So this is going to mean that we have to know these axioms of an inner product. So I'm going to write them down again, just to kind of get them back on our front burner. There's actually 4 of them that we learned in chapter 5, and let's just remember what they were. The first axiom is just the one that says, if you take the inner product of a vector with itself, the inner product of a vector with itself always has to be at least 0. Remember, it's a number. The inner product of 2 vectors is always a number. If you forget that, just remember that inner products are like dot products. And when you were doing dot products from back in the calculus days, you know that the dot product of 2 vectors returns a number to you. So this is going to be a number, but at least if it's the inner product of a vector with itself, that number cannot be negative. It has to be at least 0. And the only way that it could equal 0 is, this kind of goes along with the first axiom as well. It can only be equal to 0 for the 0 vector itself, right? So that's the first axiom of an inner product. Inner product of anything with itself must be greater than or equal to 0. The second axiom, we're not actually going to need all 4 axioms to do this problem, but I want to write them all down anyway. Since we're reviewing right now, we might as well remember what they said. The second axiom is the one that, if you remember, it just says you can switch the order of the vectors in that inner product. So the inner product of V with W is always the same as the inner product of W with V. And then the third axiom is the one about factoring out constants. So if I have the inner product of, let's say, K times V with W, this is the one that says, all right, I can pull that K all the way out. So the K can come out in front. And then the last one is the one that allows me to add 2 vectors together. Let's say V1 plus V2, inner product that with W, and I get the same thing as the inner product of V1 with W plus the inner product of B2 with W. Okay, so those are the four axioms. Pretty good idea to know those axioms a little bit. Okay. The third and fourth axiom are really playing on the first slot mostly. The second slot is just W all the way through all of these terms. We did show that because of the second axiom allows you to switch which slot is first and second. If you take advantage of that, you can actually create what I would call sort of two more axioms where you put the constants in the second slots and put the plus signs in the second slots, and you can bust them apart and pull things out just the same way. So it works exactly the same way. It would be like a 3' and a 4'. There'd be two more rules down here that would allow you to do the same things as the third and fourth axioms, but in the second slot rather than the first slot. So they aren't technically axioms, so I don't like to put them in the list here. Okay. When you see a question like this, is such and such a valid inner product? You are being asked about these axioms. You're basically being asked, will the formula that they gave us, will this formula that they gave us satisfy all of these axioms? And what you have to do on something like this is actually just run through them and see, well, would they all be true for that formula? I usually like to run through them in this order. Nothing says you have to do that, but I like to run through them in this order because that first axiom is often the one that could be a red flag. It's harder for a formula to make it through that first axiom. So I like to cover it first. Let's take a look at that. So let's go through the solution here. I don't know yet whether it's a yes or a no, but let's look at this first axiom. Let's look at this first axiom. So first axiom. Is everybody with me? Are there any questions so far? We're so good. Okay. If I want to look at the first axiom, it means I'm putting the same vector in both slots. So what I'm going to do in my formula is I'm just going to put the same thing in both slots. So I'll just write it so that I can see what it looks like. A0 plus A1x plus A2x squared, inner product with itself, yeah? With itself. So I just put that same thing in both slots. And well, this really just means that all of the B's are just A's again. So if I just read my formula, it's just going to be A0 A2 plus A1 A1 plus A2 A0. So all of the B's just get replaced by the corresponding A's in the formula. I will go ahead because it's pretty obvious that we can clean this up just a little bit. It's two factors of A0, A2, and then there's an A1 being squared here. So it's A2, A0, A2 plus A1 squared. And here's my question for you guys. Is that expression going to have to be greater than or equal to 0? Or could you think of a way to make it come out negative? I didn't write it in the axiom here, guys, but of course this formula has to always work. For every vector. For every vector, this would have to be true. Do you think for every choice of A0, A1, and A2 that this would always be positive? I don't think so. I think you could make it come out negative if you chose those numbers wisely. Does somebody want to try some values for me? Like, there's lots of right answers here for what we might be able to plug in. Just some numbers for A0, A1, and A2 that would make this come out negative. What do you think we could use that might work? Go ahead.
Just make it equal to 0.
Give me some specific numbers. What do you want A0 to be? What do you want A1 to be? What do you want A2 to be? Go ahead, Oscar.
Like if we made A0 -5.
-5, there you go.
And then A2 is like 2,
2, okay, great.
and then A1 is 1.
And A1 is 1. Let's try that. So that means my vector is -5 plus x plus 2x squared. That's just putting in the A0, A1, and A2 into the notation of the quadratic polynomial. And if you have that, then what is the value here? Well, for this choice, well, you can see 2 times -5 times 2 would be -20. And to that, we're going to simply add 1 squared. So this is actually -19. And that means that that's a bad answer for us to get, which is it's violating this first axiom. And so the conclusion here is that axiom 1 fails. It's not the only choice you could have created, but it's a really nice one. There'll be lots of other values as well. Do I need to go on and look at the other axioms? Actually, as soon as one of these axioms is failing to hold, it's game over, right? The formula is flawed. It will not be a valid inner product. So at this point, we already can say no. And we are pretty much done with what we can do here. As soon as you know that it's not a valid inner product, then I really can't ask you anything else. I can't ask you for the angle between two vectors. I can't ask you to do the Gram-Schmidt process. I can't ask you to normalize anything. None of those questions would make any sense if I don't have a valid inner product. So this is kind of the end of the line. Right? As soon as you have a no here, it's like, okay, we're done. I can't do anything with it. And we move on. That makes some sense? Okay, so let me tweak this formula a little bit. I gave you this formula. By the way, the formula would have to be given. If anybody's wondering about that, you wouldn't be expected out of the top of your head to know what this formula is. I have to give you this formula and then ask you something about it. Let me try and give you a better formula. This one was not good, but I can just tweak it a little bit and make it a good formula. And then I can ask you some better questions. So let me come back over here and I'll do that. Is everybody okay with that? Does that make sense? Some of those axioms would have been okay. Right? Some of them would have worked, but all it takes is one axiom to not work, and I am basically done. Yeah. Awesome.
I didn't quite catch the second line of the first axiom. How did you get that?
I just plugged into this blue box. So A0, A1, A2, right? Then the second vector has a B0, B1, B2. But for the first axiom, I don't want to use B0, B1, B2. I have to use an A0, A1, Z2 again. So I just took this formula and I literally took all of these B's and replaced them with the corresponding A's again.
Oh.
Yeah, that's all it is. That's a good question. Yeah. Something we've got to be able to do. Okay. So let me take another example. That's it for problem 6. Let me go to another problem from the review session, which is going to be number 7 now. And I'm going to ask you here. So I'm going to take the same vector space, guys, P2 of R. And I'm going to define my inner product again. So this will be A0 plus A1x plus A2x squared. Inner product with B0 plus B1x plus B2x squared. But this time I'm going to give you a slightly different formula. Namely, I'm going to give you A0 B0 plus A1 B1 plus A2 B2. Okay. As it turns out, this time it is a valid inner product. So I could ask you here, actually, I'm going to do several parts to this question. So the first part to this question is going to be to show that this inner product is a valid inner product. I'll start by doing that. try to show that this is a valid inner product. Now, to do that, actually, if it is valid, then I've actually got to check all 4 axioms. I'm not likely to ask you that tomorrow. I might ask you to check 1 axiom or maybe 2, but all 4 would take a long time. Let me just check the first one, since that was the one that gave us all the trouble in the example a minute ago. Let's check the first one. Do you see the difference, by the way? It's very subtle. It's just the subscripts. Instead of A naught B2, now I have A naught B naught and A2 B2, right? So it's almost the same thing as before, but what happens now, guys, if we check our first axiom, if we check this first axiom, if I go in here and I do, the inner product of A naught plus A1x plus A2x squared with itself, I just copy it twice there. Well, this time, if I change all of the B's to A's, I'll just have A naught plus A1 plus A2. It's literally just replacing the B's with the same A's again. And this one, if we clean this one up, is A naught squared plus A1 squared plus A2 squared this time. Yeah. And is everybody comfortable if I'm adding up a bunch of square numbers? It's definitely going to be greater than or equal to 0, right? We can check that one off. Definitely greater than or equal to 0. And this one would be equals to 0 only if A naught and A1 and A2 are 0. So that's the whole extent of the first axiom. Yeah. Okay. Does anybody want me to check any more axioms, or is this enough to kind of give you the idea how this works? Oscar?
Can we do the addition?
The last one? It's the one I hate to do. It's the messiest one, right? I think, how about this? I'll make you a deal. I'm probably not going to ask you to do that tomorrow. Let's make that a deal. This 4th axiom is really tedious to check. So, well, what I probably am more likely to do is what I told you a minute ago, which is I'm probably going to give you a choice. If I let you choose which axioms to focus on, I highly recommend you stick with 1, 2, and 3, just because it's less work to write them out. Okay, so I think I would rather, it would take me half of a board to write that all out. So let me do maybe like the 3rd one would be not so bad. Like the 3rd axiom is maybe worth showing it to you, just so you can see one more case. This is more like what I would ask. Choose 2 of the axioms and verify those 2. So let's say I chose the first one and the 3rd one. This time you have a K, and the K is kind of in here with this first slot. So you'd have something like K times the quantity of A naught plus A1x plus A2x squared. And then you still have a B naught plus B1x plus B2x squared. And what you need to do here, guys, is you need to get the K pulled out of it. You need to get the K pulled out of this thing, but be careful not to just yank it out automatically. I need to see how does it come out through the process. So really, if I really want to do this carefully, I should actually first just distribute the K into the terms of this first polynomial. I should distribute that K in there. The second slot, I can leave it the same. And kind of running out of room even for this. Now I'm in a position to be able to use my formula here. How does the formula work? First constant term times first constant term, and then first x term times first x term, and then first x squared term times x squared term. So this is just going to be Ka naught times B naught, and then Ka1 times B1, and then Ka2 times B2. And even for this axiom, I don't have enough room. So let's make a little more room here. Yeah, so now what are you gonna do next, do you suppose? Exactly. You just want to factor the K out of what you got here. And that's exactly right. So this just becomes K times the whole thing, A naught, B naught, plus A1, B1, plus A2, B2. And now what you're looking at is literally just K times the inner product of the two original vectors. So now I can finish it up by writing that down. So that checks it off for that third axiom. So it's a little bit of work to write that down, but that's what you have there. Okay. Great. So far, so good. So make sure you know the axioms. It's really helpful for this sort of a problem. Let's do a part B. This was only part A. Show that this is a valid inner product. Let's do something else. Now that I have a valid inner product, I can start asking you other cool questions, right? So maybe what I'm going to ask you now is part B, find the angle between P of X, which is going to be 1 minus 2x plus 2x squared, and Q of X, which is going to be 2 minus x squared. Okay. So a little more room over here too. Right. So to do this question, now that we have a valid inner product, we just need to remember the angle formula. I sometimes get surprised if people don't always know this one because this is actually just stolen from calculus. It's the same formula that you would have seen in your 250A class. It's just basically the cosine of theta, which I'm going to rewrite it as the theta equaling the inverse cosine. What you have to do is create a fraction of the inner product of the two vectors, in this case, P of X and Q of X. And then in the denominators, I need to write down the norms of P of X and Q of X. Yeah, so this is what we would do to find the angle. Obviously, we're not going to do this test with a calculator, so you'll just be expected to get some kind of an expression for theta. You're not actually going to find theta as an actual angle here, but this is the formula for doing it. And so we just need to go through and calculate these things, right? So let me just start into it. In the numerator, I'm just going to take the inner product of the P of X and Q of X. Now, how do I do that? I got my formula here. This is how I take the inner product of two vectors. So how does it work? Oh, I multiply the constant terms, and I multiply the x terms, and I multiply the x squared terms. So let's take a look. Constant terms, 2. X terms, 2. X squared terms, -2. Everybody with me on that? 2 plus 2 minus 2. That's the inner product using this formula, right? A naught is 1, B naught is 2. A1 is -2, B1 is -1, A2 is 2, B2 is -1. If you crunch that out, you get 2 for an answer. Okay, so that's what you're getting in the numerator. For the denominators, I have to do these norms. So this is a good chance to remind everybody the formula for a norm of a vector. The formula for the norm of any vector is the square root of the inner product of that vector with itself. Right. So we would just need to apply that here for the norm of P of X. I'm going to have the square root of the inner product of P of X with itself. And let's see. So the inner product of P of X Where's P of X? This is P of X, right? With itself, so that's gonna be 1 times 1 plus -2 times -2 plus 2 times 2, right? So this is gonna be the square root of 1 squared plus -2 squared plus 2 squared. Everybody see where I'm getting those numbers from? It's just these coefficients. A 1, a -2, and a 2. I square them and add them up. So that comes out to the square root of 9, which is actually just 3. So I'm going to end up with a 3 down here in the denominator of my arc cosine formula. And then I got to do Q of X as well. So the norm of Q of X, this one will be, again, the square root of the inner product of Q of X with itself here. All right, and for that, I have to go find my Q of X. Here's Q of X. A0 squared plus A1 squared plus A2 squared, right? So it's really just this, right? So from the first axiom, so it's just squaring up the components of this term, so of this polynomial. So 2 squared plus -1 squared plus -1 squared, and that becomes the square root of 6. And I got to put my radical 6 now on the bottom here, like that. And so my final answer for the angle would be the arc cosine of 2 over 3 radical 6. And guys, you do not need to simplify that. You can just leave that as is. I will totally give that 100% credit. Doesn't need to be changed any better than that. Without a calculator, that's as good as it gets. Okay. That's finding the angle between two vectors. What do you guys think? Feel all right about it? It's totally plug and chug. Actually, this chapter is mostly plug and chug. I'm only going over it because it's been a while. Let me write down one more part. There's a part C, and then I think I'm going to feel pretty good about chapter 5. So part C, which I'll maybe write it down over here, is to find an orthogonal basis for, I'm going to call this S, and S is going to be the span. It's going to be the span of 1 minus 2x plus 2x squared, comma, 2 minus x squared. Okay. What does this question suggest you're going to need to do? If you see a question like this, find an orthogonal, blah, 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 it's always the Gram-Schmidt process. And I'm going to give you these Gram-Schmidt formulas on the front of the test. So you won't even have to like study this. And I wouldn't even study this that much in advance. The only way you can sort of blow this question is if you don't recognize that you're using the Gram-Schmidt process. As soon as you know that it's the Gram-Schmidt process, it's really not bad. You just write down, here's V1, here's V2, and then on the front of your test, it's going to tell you what to do. You're going to replace these two vectors with an orthogonal set of vectors that is a basis for this span. Okay? So these are the two vectors. And by the way, they're the same vectors we used in part B, so we will already have most of the work done here. Well, all I have to do is, so for the solution, by the way, if you just write down, I mean, I don't recommend, I mean, you guys should be able to do better than this, but if you just write down Gram-Schmidt on your paper and go on, I can give you a couple points for that. So write that down first, and then hopefully this is not freaking anybody out because it's just a simple thing, guys. There's a formula for the W1 and the W2, and it will be given to you on the front of the exam. So you don't have to even learn this right now. You can just be ready to go. You just have to know that it's the Gram-Schmidt process. So the first W1 vector is just the same as the V1. So that would be, 1 minus 2x plus 2x squared. For the W2 formula, again, it'll be on the front of your exam. I happen to have it memorized, so I'll write it down for you here. It's V2 minus the quantity of the fraction of the inner product of V2 with W1 divided by the norm of W1 squared, all multiplied by W1. So I'll just put that there for you. Again, you don't need to know this from memory because I will provide these Gram-Schmidt formulas. And now we're just going to plug everything in. So V2 was 2 minus x squared. That's V2. And then minus, then we have to make a fraction here, guys. Now, in the numerator of the fraction, we're actually just taking the inner product of V2 with W1, which means we're taking the inner product of these two vectors. Well, we already did that. Over here, the inner product of these two vectors was 2. It was in the numerator of this dot product, so that's already just a 2. And then on the bottom, I have to put the square of the norm of W1. Well, remember, W1 is the same as V1. And V1 is just my first polynomial. I bet we found the norm of that already. It was 3, right? So in the denominator over there, I'm going to write 3 squared, which would just be 9. Would just be 9. And that's multiplied by W1, which is 1 minus 2x plus 2x squared. Okay. And I would honestly accept that as an unsimplified answer. If you really wanted to clean this up, you'd have to expand this out a little bit and turn it into a simple little polynomial. But honestly, if you've shown me that much of the work, I pretty much believe that you know what you're doing on this type of problem, and all the calculation is there is good enough for me. Yeah, that's going to be good enough for me. So that's the Gram-Schmidt process. If you see find an orthogonal basis, you want to write down Gram-Schmidt. Even if I say find an orthonormal basis, just to remind you about that, if I ask for an orthonormal basis, once I've got my W's, I would need to normalize them, which means divide by their norms. So like W1 had a norm of 3. So we would have to take this 1 minus 2x plus 2x squared and just divide through by 3, right? And then I'd have to figure out the norm of this. That doesn't look very pleasant. I'm not going to do it. But you'd have to figure out the norm of that second W2 vector, which has got some messy fractions in it, and get your answer from there. Question? Yeah.
You happen to ask for one, is it okay if we just leave it? All that work, I guess, unsimplified.
Like if you left it like this, I'd probably take it.
Oh, okay.
If you didn't actually reduce it, but I need to see enough work that I believe that you know what the norm is, all that jazz. Yeah. Okay. Other questions on that? Okay, that's pretty good. Let's see, where do I want to go from here? I'm just trying to make sure I'm covering everything as best as I can cover stuff. There is something else I wanted to do. Oh, yes. Let me, I'm going to do a problem that's like one that I did last night, except I'm going to change it slightly just because I see there are a few people who are here again tonight. So I'm just going to tweak it a little bit just to make it fun for everybody. Change subjects a little bit. So let's do this problem. And there's definitely going to be something similar to this. I just know it because it's a very popular kind of question. I'm just going to write old final here. You'll see this on the sample finals and so on. I'm going to create a subspace and ask you to show it. So let's suppose that, let's let V be equal to P3 of R Again, this is a tweaked up version of a problem I did last night. And then I'm gonna let S be the set of P of X in V such that P of 1 is equal to P of -1. And I have a few things I want to do with this problem. I would like to start by showing that S is a subspace of V. So show that S is a subspace of V. Let's see if we can do that much first, and then we'll go from there. What am I probably going to ask you after we show it's a subspace? Well, it's like always the next thing I ask. Find a basis for it. Exactly. So we'll show it's a subspace first, then we're going to try to find a basis for it. All right, super. So let's go through this. This is the heart and soul of chapter 4. Okay. So yeah, let's try it. What do we need to do to show that this is a subspace?
It matches the zero vector axiom and then addition and scalar multiplication.
Okay, so closure under addition and closure under scalar multiplication. Let me say a quick word about the zero vector check. There is a zero vector check that we learn, and where that's useful is if you don't think you have a subspace. If you don't think you have a subspace and it turns out the zero vector check fails, you win already, right? It's already not a subspace and you can just say that. If the question has been already set up this way and it says show that it's a subspace, then you actually already know that the zero vector check, if you did it, it would pass. If it didn't pass, you wouldn't be getting this question, right? So if I'm asking you this question, then it must mean that that zero vector check passes. And so in that case, it's not really worth your time because you're just going to check it and then, well, you're back where you started. I got to do the closure under addition and scalar multiplication. So if this question said, is S a subspace of V, then I would probably think about the zero vector check because it's so easy to do it. By the way, what is this? Okay, I just got done explaining that we really don't need to do the zero vector check here, but let me just take a moment. Like, what would it look like if I did actually check it? I need to understand what is my zero vector in this universe. It's literally the polynomial 0. Like, so my zero vector here would be 0x cubed plus 0x squared plus 0x plus 0. That's how you would write it as a vector. And if I want to draw a picture of it, the zero vector would just be literally this blue line right here. That is my zero vector. As a graph, it would look like that. And you can ask yourself, okay, if I plug in 1 on that graph, is it the same as plugging in -1 on that graph? And it absolutely is. Here's P of 1 and here's P of -1. They're both equal to 0. So it does pass that zero vector check. Again, we don't really need to spend time on the zero vector check here because we know it's a subspace. But it's a great thing to know if the question asks you yes or no, am I looking at a subspace? If that zero vector check fails, it's game over already and you save a whole lot of time. It fails the zero vector check, it's not a subspace. We've seen tons of examples of that, right? It's a very, very common topic here. But this one is already framed as something that's going to be successful. So everything's going to check out. Let's just jump into the closure under addition. Because that's where the real heart of this calculation is. I'm going to check the closure under addition here. Well, so how does that work? I have to start with 2 vectors in S, and then I'm going to add them together eventually. So you can use whatever notations you want. Now so don't write this down yet, guys. If you wrote this down on your paper right now, it's not really wrong, but it's really a confusing choice of letters. A and B looks like a matrix, right? This problem is not about a matrix, this is about polynomials. So I would rather see, now let's write down something better. I would rather see you write maybe f of x and g of x. This would be like a reasonably good choice. Just to write that one down. Okay, let f of x and g of x be in S. Okay, let's write down what does that mean? Okay, I know the temptation is you want to add them together immediately. But before you add them together, let's write down the condition that is, this is the part people often don't put enough emphasis on when they're writing it up, and that's the key. So then f of 1 equals f of -1 and g of 1 equals g of -1, right? We can say all of that. Okay. And then now I'm ready to add them together. I'm going to take f plus g, and I just want to check, is it still in S? Well, how am I going to know? The way I test if it's still in S is I look at my condition. What happens if I plug 1 into that? Right? Now, the way you do this calculation, if I have two functions adding together applied to 1, that is just f of 1 plus g of 1. That's just the definition of it. It's almost like you're distributing the 1. Okay, and then f of 1 can be replaced with f of -1, and g of 1 can be replaced with g of -1. And then you can say, oh, okay, yeah, that's equal to what I would get if I took all of f plus g and plugged -1 into it. This is looking pretty good. For closure under addition, it looks like f plus g has the required membership condition. If I plug in 1, it's the same answer as if I plug in -1. So this is the calculation you would want to show me. Would I be done right now? Or should I write something else down over here? This way?
It's right there, it's closed, not closed, oh yeah, closed under B. Or S.
So yeah, we're checking closure under addition, but what's the thing that sort of is my punctuation at the end that proves it? Andrew?
Am I right? F plus g of x is goes within S.
Exactly. This is just f of x plus g of x is an element of S. That's just like your conclusion. And I keep talking about how I'm going to pull out my red pen if you don't write that down. I won't take off a lot, but I might take off a point if I don't feel good about your answer. So it's good to include that one. It's a good thing to write that down. Okay. So f plus g is in S. For some reason, there's a lot of people that like to write S as an element of V on their papers. I see this all the time. I don't know why people are writing that. It doesn't really make any sense. So it should just be in terms of S, not in terms of V here. There's no mention of V. V is just the ambient universe that this problem is framed in. It really doesn't play a big role in the solution. Yeah, Bishop?
If there was no conditions, is that when you would have to write out like the general form of the poem and then
Oh,
with that?
I thank you for bringing that up. Did you notice here, guys? I never wrote down. I mean, in P3 of R, you're normally thinking your polynomials are going to be like ax cubed plus bx squared plus cx plus d. And you notice I never wrote any of that down here. The reason that I was able to avoid writing all of this messy stuff down is that the condition that was given to me didn't require me to get my hands on those A, B, C, and D coefficients. I was able to write everything just in terms of this more abstract presentation. It was provided to me in this abstract way, so I'm doing my write-up in that abstract way. So that's the reason that you don't see me spelling all of this out. If my condition here, I could have given you a totally different problem where maybe S was written out in that form to begin with. I could have done something like this and said S is this set such that, I don't know, A plus 2B minus 3C adds up to 0. I could have done that as my subspace. If this was the problem I was asking you, then yes, you would need to write your f of x and your g of x out as term by term in this expanded notation because that's how the problem was phrased. So it's kind of, you just kind of mimic the way the question was asked is sort of how you want to use the notation for it. Yeah. Okay. Anyway, so I didn't want to do this because it'd be so messy. I chose something a little bit easier. Okay, the other part of this is the scalar multiplication. Let me just run through that really quick and then we'll do a little part B on this. I think we're coming along great here, guys. 2 hours down, at most 1 more hour. And if you need to leave early, it's totally fine. I totally get it. I'm not trying to hijack anybody's time tonight, but this is just the nature of it. There's a lot to go over. For the scalar multiplication, the way I like to set this up is we grab a scalar, I'll call it K. That's usually my letter of choice for scalar multiplication. Let K be a real number. And then I'm just going to say f of x as above. So I'm just going to like steal the same f of x that we've already been working with. And we're just going to jump into this part here. Yes, Oscar.
Do we have to change the function or can we keep it as p?
You could use P and Q here. I even said a moment ago you could use A and B if you wanted. It would be a bad choice because it's confusing. But you can choose those letters. If you want to use R of X and S of X or A of X and B of X, it's totally okay. Yeah. Okay, so on this one, I'm now going to look at K times F. I'm going to do the scalar multiplication. And what I want to do is check this condition. If I plug 1 into it, is it the same as plugging -1 into it? Let's check it. Let's plug 1 into that thing. Now, the way you do this calculation is you just do f of 1 and then you multiply it by k. So I'll just kind of pull the k to the front here. But as you can see, f of 1 is just the same thing as f of -1. Because that was already what we were starting with that we had set up earlier. So I'll just steal that same statement. This is why doing f of x as above is so nice. You get to use all that stuff from over there. And now this is just k times f of -1, right? We can go ahead and go back to the way we had it set up in the first place. And at this point, you want to take a broad view of it. Where did you start and where did you finish? K times f of 1 agrees with k times f of -1. That's exactly what gets you into S. You belong to S if when you plug 1 in, it's the same as plugging -1 in. And so I'm just not going to get Dr. Annan's red pen out if I just make sure that I put my little conclusion sentence there, I should be good to go. Should be good to go. So k times f is in S, and so we are good to go. So far, so good? All right, so we can do problems like this, I hope. And then, of course, as I mentioned earlier, I am now going to bring to you the part B of this, which is the natural follow-up. Find a basis for S. And I could probably ask you for the dimension as well, but we'll just talk about that once we find it. So now, as much as I've really tried to avoid having to get my hands messy on the terms of the polynomial, to do this part of the question, we really do need to write out the p of x in terms of these different powers. I got away without doing that all the way through the blue writing so far on part A, but for part B, I absolutely have to go there, right? So I'm going to start this one off for the solution to part B. I'm going to just basically go ahead and write it out as ax cubed plus bx squared plus cx plus d term by term. There's really no good way to avoid that anymore. Now, if you were to tell me that this is the form of the vectors that you want to create your basis from, I would tell you that actually this is only the form for the vectors in V. the big universe V, P3 of R. If I say, what does a polynomial in P3 of R look like? That would be a great answer, okay? But I'm actually trying to find a basis for S, which means I need to write down the form of the vectors in S. And if I don't take advantage of the condition here, I'm probably not capturing what the vectors in S look like. So what you will want to do here, and this is a good starting point, but I need to take it another step further and plug in 1 and plug in -1 into these functions and set them equal to each other. So let's just do this. P of 1, if I just put in 1 for x everywhere, I am just literally going to have a plus b plus c plus d. And then when I plug in -1, everywhere I see an x, now I'm going to plug in -1. Okay, so -1 cubed is actually a minus on the a term. I still get plus on the b term. I now get a minus on the c term, and I still get a plus on the d term. And I need to set these equal to each other. So I'm just going to set a plus b plus c plus d equal to -a plus b minus c plus d. Okay, and this can be kind of cleaned up a little bit. There's a b on both sides, and there's a d on both sides. So I'll kind of cancel those. And then, you know what I'm going to do? I'm just going to add the subtracted terms over to the left side. So it becomes a 2a plus a 2c, adding up to 0 here. This becomes the main condition on these polynomials. Now I've expressed it not abstractly like we originally were given. Now it's being expressed really down in the nitty-gritty, in the trenches of what the forms of these polynomials looks like, right? So this is basically just telling me that, well, actually, honestly, I just want to play it straight. The way I would normally set this up, as you know, is I would make a matrix out of it. It only has one row because there's only one equation, but my unknowns, this is a little system, guys, with one unknown equation, and I can circle a pivot there on that a variable. And what I see is that, well, B, C, and D are all free variables, right? So B, C, maybe I'll write it here. B, C, and D, they are all free. Let me just write them as R, S, and T. It's only A that has a pivot on it. I can solve for A pretty much just straight from here. A is just negative of C. So let me write that down. A is negative of, I guess it'll be S, the C variable, which is S. Okay, so with that understanding, now I'm going to rewrite my P of X in the better form that is incorporating all of this, okay? Maybe we should do it over here so that we are ready to finish this up. We're almost done already with this, but the key thing is a lot of students, I've seen this so many times, they just write down this P of X and they don't incorporate the condition here, which is part of what you need to have inside of your calculation, right? So, okay, so let's go ahead and write down the form that we really want to use based on what we have here. So P of X now, it's A, which is negative S times X cubed, and then plus B, which is R times X squared, plus C, which is S times X, and then finally plus T. That's actually the form we want to work with. And I need to bust out my variables now, right? Once I get the form of my vector, I'm going to bust out my variables. I'm going to bust out the R. I'm just going to do it in alphabetical order. When I bust out the R, I get an X squared. When I bust out the S, I get negative X plus X. And when I bust out the T, I just get 1. You just bust all of those terms out like so. And from there, how do I get my basis?
Squared becomes
comma, negative x.
And then comma one. That's exactly right. That's it. That's it. And so what is the dimension of S, by the way? It's just how many vectors are listed here. Even if you got this completely wrong, if I ask you for the dimension and you give me the answer based on what you wrote for your basis, and if it's correct based on your answer, I give you credit for that. Full credit for that, actually. So it's always good to push through on something like that. Okay. So that's notice that the dimension of V itself would have been 4. But because of this condition, it got knocked down to 3. So the subspace is only 3-dimensional because this basically it's a little bit harder to belong to S than it is to belong to V. The membership condition is tougher to meet, and so S is smaller. If it's smaller, the dimension goes down. Right, so it's down to 3 dimensions here. Yeah, that's how that works. Questions on that at all? Okay. Guys, bear with me for just a second. I have a specific thing I want to find. I did it last night, and I really think I should do it again. Why I can't find this thing. So, do you have the notes from last night? One of you take notes last night?
Yeah.
Are they on a paper somewhere or are they typed up? They're typed up,
I wrote them out.
but they're on your screen there.
Yeah.
Where is this? I need to, oh, I found it. Okay, I found the problem I wanted. I want to do the problem, I'm gonna do a new problem, but it's basically the one that on the third midterm was the one that overall people had the most trouble with. And it was maybe a little bit out of left field, but I hopefully, once you see how to do a problem like this, you'll see it's not so bad. So this is also off of an old final. Let me do this example. So I'm going to let S denote the solutions to, and then I'm gonna have a differential equation here. And here it is, guys, x squared y double prime plus 2xy prime minus 2y equals 0. So I'm gonna let S denote the solutions to that. Okay. Now, I would like to ask you which of these is a basis for S? I'm going to give you some options here. So the first one, I'm going to call it S1. It's kind of like a multiple choice question, basically. S1 is going to be 1 over x squared, comma, x squared. And then the second set is S2. This is going to be the set of 1 over x squared and x. And then S3 is going to be the set of x and x squared. And then I need a little more room. Let me come over here to write the next one. S4 is going to be the set of 5x minus 1 over x squared, comma, 2x plus 7 over x squared. Okay, go ahead and write that down. And then S5 is just going to be the set of x itself, just x. Okay, so there was one like this on your midterm. It was in the more conceptual section. It's more of a concept. Well, it's kind of a mix. It has some of the concepts, but it's also calculations as well. Let's see if we can make sure everybody can do a problem like this. The first thing I want to say about this, actually, I think I'm going to work on it right next to it here, if that's okay. So I've already copied this down so far. The blue part, okay, I'm gonna get rid of that then. The first thing I want to say about this, guys, is actually this differential equation is not one that we learned how to solve this semester. So the purpose of this problem is not for you to actually solve the differential equation. You're not going to know how to do that because we didn't learn it. Now, if I really wanted to, I could give you a trial solution and have you plug it in and see if you could get it to work. Right? That we have done before, but I would have to provide that to you. It would have to be kind of laid out. Here's the steps you need to go through. So you would not be trying to figure out how to solve this equation. That's not the purpose. The question is, which of these could be a basis for it? And we're going to find out there's more than one correct answer here. Can anybody tell me anything about what I should be looking for in a correct basis for something like this? Levi?
The order of your differential equation.
What is the order of this differential equation?
2.
The highest number of derivatives, right? That's 2. I usually call that n. So it's a second order differential equation. So do we know anything about how many basis vectors we should have for a second order differential equation? Exactly 2. So that the order of the differential equation tells you how many basis vectors you should have. So I can go through my list, and if there's any sets that don't have 2 things in them, I don't even have to take a breath. I can cross them off. So S1, 3 things in there. Cross them off. I'd probably write a little note, too many vectors. Right? And then notice S5. Only 1 vector in S5, so this would be too few vectors. That's not going to work either, right? So if I don't have the correct number of vectors to begin with, I can cross them off immediately. Now the other 3 sets do have 2 vectors each. That doesn't automatically make them into a basis. For instance, just because I have 2 vectors doesn't mean they're a basis. What if they were scalar multiples of each other? That would be bad, right? Now, if you look at this, none of these are actually scalar multiples of each other. Like these 2 are not scalar multiples. These 2 are not scalar multiples. These 2 are not scalar multiples. So what you're looking at, they really are Li. Each of those sets, S2, S3, and S4, they are all Li. If I wasn't sure about that, if I wasn't sure if my functions were Li, what's my go-to for testing for linear independence of a set of functions? Oscar. It's the Wronskian. It's the Wronskian. So if we needed to, we could use the Wronskian. Here we don't really need to, because I can just see that the 2 vectors that I'm looking at on each of these sets is not a scalar multiple of the other one. But in general, we can use the W test for linear independence if necessary. So if that would be helpful, we can certainly use the W test to test for linear independence. Yeah. So that's one issue, because actually out of these 3 options, they're not all going to work. There's something else that could go wrong. Yes, they might have the right number of vectors. Yes, they might be Li. What could go wrong? What could make some of these other sets not correct? If they don't actually solve the equation. Exactly. If I plug these into my equation, now that everybody can do, right? If I give you a function and I say, hey, does this solve the equation? That you can do, even if you've never seen this type of an equation before. So let's just try it. What do I have here? I have a 1 over x squared, right? So let's just try that one. Let's try 1 over x squared. Okay, so I'm just going to plug it in. On the left side, I have x squared times 1 over x squared with double derivative, right? And then it's going to be plus 2x times 1 over x squared with a single derivative. And then it's gonna be a minus 2 times the 1 over x squared. And let's just see, is that going to be equal to 0? That's the question. Because on the right-hand side of my equation, it's supposed to be equal to 0 over here. So let's just check it out. Let's just try it and see if it works. So we do have to take a couple of derivatives here of 1 over x squared. I'm gonna just scribble up here on the top, if you don't mind, guys. The first derivative of 1 over x squared, I could write that as negative 2 over x cubed, just using the power rule. The power rule on the 1 over x squared would give me negative 2 over x cubed. And then if I want to go to the double derivative, then I have to take another derivative of this one, which is actually going to be 6 over x to the 4th. You can also rewrite everything with negative exponents if that's easier for you, but I kind of like to just leave it as fractions, okay? So the double derivative of 1 over x squared is actually 6 over x to the 4th. I'll put that in right there. And then plus 2x times the first derivative of 1 over x squared, which is negative 2 over x cubed. And then minus 2 over x squared, like that. And I'm just going to take a look at this and just see, does it cancel out to 0? Well, 6 over x squared minus 4 over x squared minus 2 over x squared. Absolutely, I'm not losing my mind. That is actually 0. Should just be 0. So that does check. 1 over x squared is a valid solution. But that's not the only thing I need to check. Of course, I have other things I should also be checking. The other ones go a little easier though. I'm going to go kind of quickly through these other ones. Actually, the way that I could really make this into a good question. So it turns out that the correct trial solution to use for this type of differential equation is x to the r. And it turns out that when you plug it in, you can solve for the values of r that work. And negative 2 does work. The other one that's going to work, I think, is r equals 1. If we just take x to the first power, just check it out, guys. Let's just try x itself. I'll do this quickly. You just get x squared times the derivative of x, the double derivative of x, plus 2x times 1 derivative of x minus 2 times x. If you crunch that out, take a couple of derivatives of that, I promise you that is going to equal 0. So both 1 over x squared and x, they are solutions. They are Li. It's the right number of vectors. This is sounding like everything's working out, right? This is a basis, right? This one we should be circling. This is a correct basis. 2 linearly independent solutions, which are both in the solutions set, okay? Now, where things go wrong, guys, where things go wrong, and maybe I'll save you the aggravation of it. If you try x squared into the equation in the same manner that I've just been showing you, it turns out it doesn't work. It will not give you 0 on the right-hand side, which actually means that although S3 has the correct number of vectors, and although they are Li, the x squared is an invalid solution for this differential equation. X squared doesn't work. We could just make a note of that here. I'll save you the boring calculation of that, but it doesn't work. It doesn't work. What do you think about the S4 over here? It's not? Did you try it? Just right?
Since number x squared is and x works. This is just a linear combination of both of them, so it should work.
These are linear combinations of two things that already work. And guys, we're talking about a subspace right now. The solutions to this thing are a subspace. If you remember, it's closed under addition and scalar multiplication, i.e. linear combinations. So these two These two solutions are just linear combinations of the two that we already checked. So this is going to work, actually. Now, if you're really not comfortable with that, you can, of course, just plug those in also. Like I can take two derivatives of this, take two derivatives of this, plug them in just the way we've been trying these other ones, but it's gonna take you more time. I would rather just use my knowledge of linear algebra to say, hey, if I've got two solutions already checked, any combination of those solutions will also check, will also work. So S4 is just linear combinations of S2, and we should be circling that one also. Exactly. So that's the answer. The S2 and the S4 would be valid bases for S. The other ones are not, either because they have the wrong number of vectors to begin with, or because one of the vectors isn't even a solution, which is kind of a not even getting to first base, so to speak, on that other solution. Okay. Is that okay with everybody? Yeah, yeah.
Can you skip over this by just knowing you have to use x to the r and solve?
So by doing this process of solving for the r's, that will show you that 1 over x squared works. And it will show you that x works. So this would be good enough for circling S2 and S4, but it wouldn't be, by itself, it would not be enough to explain why you crossed off the other ones. So I would really like to have reasons next to all of these things. Okay. Even on the third midterm, guys, even after I kind of really tried to make a big deal about it, I still saw a lot of people just crossing off stuff with no written explanation at all. Like, those, is T 1-to-1 onto both or neither, and people just put a little X next to two of them. And I know you know it. Oh, V is bigger than W, so it can't be 1-to-1. And so it can't be both. And so you're crossing those off. But you should really write a little bit down for me, so I can be sure to give you credit for it. Otherwise, I'm like, well, did they just guess this? Or because I'm not a mind reader. Unfortunately, I can't. I know you probably have it right in your mind, but I just need to see you do it. Okay. Actually, speaking of that, I haven't done anything on linear transformations. I think maybe I would like to. Actually, that first problem on the midterm could have been a little better, but that's okay. We have redemption tomorrow. Basically, kernels and ranges, we got to get this clear. The kernel is a subspace of V. So if my V is polynomials, my kernel should be polynomials. And my W, the range is a subspace of W. If my W is matrices, then my range should be matrices, right? They have to be in the same notation. So let's try one, and let's take a fresh problem. This is off of an old final. So even though this was a more recent topic, I'm going to kind of go over this one, if that's all right, just to really make sure. So let's define T from M2 of R over to P2 of R via T of A, B, C, D equals, and then I'm going to make an equation, A minus 8B plus C, and then plus 2B minus 3C plus D times X. And then the last term is going to be plus 2A minus 10B minus 7C plus 3D times X squared. And I have about 3 parts here. The first part A, is going to just be to show that T respects scalar multiplication. So remember, guys, that strictly speaking, before we can talk about kernels and ranges and 1-to-1 and onto all those other concepts, before we can do that, we have to know that we're looking at a linear transformation. A linear transformation is one that respects addition and respects scalar multiplication. So this was off of an old final, and I chose to just ask the students to check the scalar multiplication part only. So just, we're gonna trust that the addition part works, but if you wanna check it, later on, you can. But for this one, I'm gonna focus on the scalar multiplication. So the way that that looks, so let me just remind you here, guys, what you're going to be checking is that T of KV is equal to K times T of V. This is what it means to show that T is respecting scalar multiplication. Okay, so let's get to it. What I'm gonna do here is I'm gonna start off with the part on the top, which is where I have the K inside the parentheses along with my vector. So I'm gonna start with this left side, T of K times A, B, C, D. Okay? And then what I need to do is hopefully get the K factored out. But let's not jump to the answer too fast. Let's derive that the K can be pulled out. Before we can pull it out, we actually have to start by putting it in. It's kind of counterintuitive, but we need to get the K on the inside. So the matrix becomes KA, KB, KC, KD. Once you have a single matrix in your hands, then you can actually use the formula for T. Everywhere I have an A, I now have to put in KA. Everywhere I have a B, I have to put KB. C goes to KC and D goes to KD. So let's put this in here. Everywhere I have an A, now I'm putting KA. Everywhere I have a B, I'm gonna put KB. This is a fair bit of writing. I picked a bad function. It's kind of messy. But it's not hard. It's just, I need a little bit more room. So I'm just gonna go down the board here a little bit, guys, just to make this all fit nicely. So that's the X term. And then on the X squared term, I have to put the K with all of the A, B, and C again here as well. So I'll just go ahead and do that, like so. And so that would be what you would have, and I really ran out of room pretty fast on that. Let me come over here. The nice thing about this kind of a problem, guys, is you know what you're supposed to get. You're supposed to get this K factored out. So if you kind of know where you're going with it, it can really help guide you in the steps that you're going to write down. So in this case, I hopefully now realize that there is a K absolutely everywhere on the right-hand side here. So what do you suppose I'm going to want to do? Factor it out, absolutely. There's a K everywhere. Let's just pull it out completely. I'm gonna pull that K all the way out. And when I do that, guys, I'll get A minus 8B plus C. And then on the next term, I'll get 2B minus 3C plus D times X. And then the last term is 2A minus 10B minus 7C plus 3D, all times X squared. It's a fair bit of writing, but it's not anything shocking. It's not a surprising thing that we're doing. And the point being now, guys, is that you have the K totally factored out. The big bracketed part is just back to the formula that we started from in the question, T of A, B, C, D. So now we are in good shape on that. Good shape on that one. Okay, so far so good. You can see why I didn't ask the students to check that T respects addition. That would be like double the notation. It would be much harder, much longer. Wouldn't be that interesting, but it would be much longer. Okay, so now we got to go to the part that is sort of more related to what the third midterm was about, which is for the next part of the question, I would like to find a basis for the kernel of T and the range of T. Okay. Yeah, so for the kernel of T, Now we're just working with the original equation, and the way you find the kernel is you just set it equal to 0. Yeah, set it equal to 0 here. So for the kernel of t, I'm gonna start with that. Just gonna set this thing equal to 0. So what that means is that you know, a minus 8b plus c plus 2b minus 3c plus d times x plus 2a minus 10b minus 7c plus 3d times x squared. This is being set equal to 0. And when I set it equal to 0, remember, I don't mean the number 0, I mean the polynomial 0. So technically there would be coefficients there. And so what happens is, you know, the constant term has to match up with 0. The x term has to match up with 0, and the x squared term has to match up to 0. You actually get equations for each of those different terms. So what it could be, guys, we could just put it into this little system of equations. The constant term has to be 0. And then the x term has to be 0. And then the x squared term has to be 0. Oh my gosh, I don't believe it. 2 hours and 40 minutes into the review, I'm gonna have to do an ERO. I made it through almost the whole night without doing one, but this is gonna be a matrix that we have to solve now. I put this into a matrix: 1, -8, 1, and 0, augmented with 0. And then 0, 2, -3, 1, 0. And then a 2, a -10, a -7, a 3, and a 0. That's my matrix. And oh my gosh, I actually have to try to solve that. Just a quick word on this, guys, with the EROs. If you make a mistake, we can all make mistakes on stuff like this. Even I myself, I will do this from time to time. I will take the work that you have. I might deduct if you miss a minus sign or you just do an ERO and have the wrong number in there. It's not going to ruin your score. It's not going to ruin your test. Basically, I'm going to take your work and follow it through. And if you base your answer off of your work, it might be the wrong answer, but based on your work, I can realize the only reason they got this wrong was because they made a silly mistake with the matrix here. And so I'm going to give them credit for all of their knowledge about the problem. So I really want you to be vigilant here in the sense that just keep persisting with it, because there's probably a lot of partial credit to be had, even if somehow you have a mistake in the work. So in this case, I'm just gonna leave the first 2 rows the same. And what I want to do is take -2 times the first row and add it to the bottom row. Yeah. So that would put a 0 there, and then a 6. And then a -9, and then a 3, and then a 0. Yeah. Okay. And at this point, the third row just looks like 3 times the second row, and it is. So it's going to get zeroed out, wiped out when you actually go to the next step. So you have pivots here and here. My variables, I like to keep track of what my notations are. So A, B, C, and D, those are the unknowns in my problem right here. And you can see that the C and the D are free. Okay, so let me write that down. C is equal to R, D is equal to T. I'm just going to use my favorite letters for the free variables, R and T. And now we have to back substitute and solve for A and B. This is where it gets a little tedious, but we can do it. If I solve for B, I'm really using this equation. It's coming from the middle row of my matrix. If I solve for B, I just need to move everything else to the other side and divide by 2. So the B is gonna be, let's see, 3r minus t all over 2. Hope I did that right. Okay, so that's B, because 2b minus 3r plus t should be 0. So that should be B. And now I have to solve for A. To get A, I'm gonna go back to the first equation. And solving for A, I have 8b minus c. Let's write that down. A is 8b minus c. Let's plug in what these things are. 8 times b is actually just going to be 12r minus 4t. And then subtracting c, I have to subtract r. You guys can take my word for this if you're feeling a little tired about the calculation here. I will just do it for you and make your life easy. This again comes under the heading of very minor. If mistakes happen here, it's not the end of the world. So your A should be 11r minus 4t. So far, so good. So my kernel of t would be the set of, so what we have, 11r minus 4t, 3r minus, actually, let's write that as let's just write that as 3/2 r minus 1/2 t. And then we have r, and then we have t. How does that look? Everybody like that? For my kernel, A, B, C, D.
Get the bus up.
To get the basis, I will next need to bust out the variables, but even before I get that, are you happy with what I have so far? Right, this is not in the correct form. I threw this up here on purpose because this is so common. Basically, the A, B, C, and D were just listed into a column. That would be great if the vector space was R4. But look what your vector space is, guys. Your vector space is M2 of R. The kernel of T should be 2 by 2 matrices. So I sort of made a mistake here to catch ourselves on that. I should be writing it as a 2 by 2 matrix. So sorry for the erasing, but the A goes like that. And then the B would be 3/2 R minus 1/2 T, and then the R, and then the T. So we would want to express it in the form of a 2 by 2 matrix, right? That's basically what you want to do. And now I can bust out the R and the T and get my basis, right? So that's what Oscar was just suggesting. The basis would be, when I bust out the R, I have an 11, a 3/2, a 1, and a 0. And then when I bust out the T, I have a -4, a -1/2, a 0, and a 1. Yeah, so there's your basis. That look all right? So what is my dimension of my kernel here? Just 2, right? 2 basis vectors, so that's the dimension of 2. Okay. Can anybody tell me what the dimension of the range is going to be? Actually, if you know the dimension of the kernel, you can always figure out the dimension of the range because of the rank nullity theorem. So people did really well on this the other day, but just to remind you, this is the formula that is very helpful. The dimension of V is just the dimension of the kernel plus the dimension of the range. So I'm just trying to review a little bit here about this formula. And in this case, see the dimension of the kernel, we just worked it out, it was 2. I'm asking about the dimension of the range, so I'll put a box for a moment. And what is the dimension of M2 of R? It's 4, exactly. This one is a 4, so just using the equation, it's just nice to know what the dimension of your range is before you even do the range. It just makes your life a little bit easier. So notice here that my kernel was a list of 2 by 2 matrices. Okay, so now let's talk about the range. And I need some more room here somewhere for the range. I already know that I should have two basis vectors for the range. I think I just come back to here. So for the range of t, let's see, do we remember how this works? This is the one where we have to take the span, right, of a list of transformed basis vectors of V. So I'm gonna take the easiest basis for M2 of R that comes to my mind. You don't have to choose anything hard. Just make a nice, easy basis, and usually ones and zeros gets the job done. You've seen me do this before. I just want to plug in all of these standard basis vectors into a list. This is what I'm going to want to do. So T of 1, 0, 0, 0, T of 0, 1, 0, 0, and so on. I will have to use my formula, which was given over there. I'll have to use this formula to evaluate all of these results. So T of 1, 0, 0, 0 is going to have me plugging in a 1 for A and ignoring everything else. A 1 for A, ignore everything else. What am I going to have? I'm going to have a 1 right here, and then a 2x squared right here. So a 1 plus 2x squared. That's my first vector. And notice that now that we're talking about the range, we're working on W. And we're looking at quadratic polynomials. This is not surprising. This is what we should be getting right now. For the second one, T of 0, 1, 0, 0. Now I'm going to plug a 1 for B, and I'm going to ignore everything else. So I have a -8, 2x, and minus 10x squared. So that's the second one is -8 plus 2x minus 10x squared. So far, so good? I have a question for you. Do I need to evaluate the third and fourth ones? You know, we already know the dimension of the range. It's 2. So far, we wrote down 2 things. Now, if these were scalar multiples of each other, then I'd be like, yeah, we're not done yet. Because if they were scalar multiples of each other, we would be throwing something away. We would need to remove a linear dependency here. But guys, these 2 vectors are not scalar multiples of each other. So guess what? This is going to be an acceptable basis. It's the right number of vectors. They are Li because they're not scalar multiples. And so this can be my basis. If you take the time to evaluate the third and fourth polynomials, you will be creating more polynomials, which will just end up getting removed anyway. So yes, there would be a third polynomial and a fourth polynomial, but I'm not even going to bother with it. I'm not even going to bother with it. Yeah. Seem okay? All right, great. So there's your basis for the range of T. Is just one last question on this, and then I might be just about done. The third question here, part C, would just be, is T 1-to-1 onto both or neither? Because I always ask that as a follow-up. So is T 1-to-1 onto both, or is it neither? This is you saw this on the midterm, you've seen it on a lot of other problems. It's a very likely question. Even before we did all the work in blue, just looking at the question itself, what could we have said about this question if we wanted to jump to this question right now? Just based on the original question, none of the blue work at all, what would you be able to tell me without even taking a breath? It cannot be 1-to-1, right? Because look, guys, M2 of R is 4-dimensional, P2 of R is 3-dimensional. So if V is bigger than W, it cannot be 1-to-1. and it cannot be both. What I would really like you to do tomorrow, if I put a question like this, which I probably will, is I would like you to give me something, even if you just write this, B bigger than W next to that, I will know that, okay, they know what they're talking about. It won't just be, oh, they just guessed the answer. I have a little bit of a justification. B is bigger than W, so they crossed it off. Okay. The only thing left to be up in the air is the onto part. At least for that, we do need to have the blue worked out for ourselves. Would you say that this is onto or not onto? Why not? Why is it not onto?
The dimension of the range is not equal to W.
Beautiful. The dimension of W was 3, and the dimension of my range was only 2. They're not matching, so this is also not onto, which means that it's neither. If it feels to you guys like a lot of these are turning out to be neither, it's because neither is always on the table. That one's always there. You're never crossing that one off in the first place. So it's very hard for T to become one-to-one or onto, or even more precisely if it was both. It would be very hard for that. Okay. Questions on that? Okay. Yeah, so anything I've been saying tonight that you're like, okay, I still need to practice that a little bit more. That's what I would do with some of the time you have left, like in the morning or something. If there's anything you want to ask me about, you certainly can. One last thing, and then I may just call it at this point, basically, because I want to give you guys some chances to rest. Last night in the review session, so on the midterm, a week ago, there was a regular defective linear system. And I think I made some little hints to you that by the time we get through the final, I'm going to have a chance to test you on like all of the cases. So, or at least try to test you on some of those cases. I'm talking about the stuff with the W's that we did very recently. I did not review that tonight. People did pretty well on the regular defective example that was on my midterm, but I just want to make sure. So last night I did a mixed eigenvalue example, and then the other one is the super defective case. So I didn't review that here. I could do one more problem and go over, probably I'd go over the super defective one because I did the mixed eigenvalue last night, and so you can watch my video from last night if you want to see that. Would you like me to do a example of a super defective system? Or do you all feel like it's getting late and you just want to call it and you think you are comfortable enough with it? Oscar?
Can you,
Can I do one?
Mm.
Sure. Sounds good. I don't even know why I bother to ask. It's always a good thing. Yeah, let's do a super defective system just to make sure. And then mixed eigenvalue is the other one that you should know about. This is the last problem I'm going to do because after this, I do want to go down to my office in case people have questions. We will wrap up with this. And I'm going to make this one up because I don't have one off the top of my head. So let's do one last example. Solve x prime equals a times x, where A is going to be the matrix -5, 0, and 0, 1, -5, and 0, and 3, 3, and -5. Okay. So the usual question, is it a system or is it a single differential equation? That's my flow chart at the top of the flow chart. The answer is this is a system. And I can tell because it's got a matrix representation. So it's a system, but it's homogeneous, unlike the one we did earlier tonight, which was a non-homogeneous system. This one is a homogeneous system. And so we need to dive into finding the eigenvalues, first of all. So actually, can somebody tell me what the eigenvalues of this matrix are without even taking a breath? Right, this is actually triangular. So it's a good chance for me to remind you that if it's a triangular matrix, the lambdas are just right down the main diagonal. So in this case, the lambdas would be -5, -5, -5. Great. Let's get to the null space for that eigenvalue. And that means I need to add 5 to the main diagonal of this matrix. So in other words, I'm subtracting -5 from the main diagonal. So that's like adding 5. I'm going to get this result here. So adding 5 to the main diagonal, I get this matrix here. And I'm going to basically move the middle row up to the top. I'm going to move the top row to the bottom. And then on the row that has a 3 and a 3 and a 0, I'm going to use -3 times the 1, 0, 0 row and add it to the bottom row, and then multiply by 1/3. And I'm just going to end up, I'm going very fast here, but that's what you're going to get. You're going to end up with pivots in those first 2 columns like that. Okay, so there we go. That is our row echelon form. And as you can see here, guys, as you can see, I only have one free variable, which is the z variable. I'll call that t. But from the middle equation, y has to be 0. And from the first equation, x has to be 0. So absolutely, this is the super defective case because I got 0, 0, and 1. I only got one eigenvector. Yeah. I only got one eigenvector, and so that means I can only make one solution. x1 of t, which is e to the -5t times 0, 0, 1. Yeah. That's the best we can do so far. Okay, I'll let you guys catch up. I know I was going a little fast, but I need to erase anyway. Once we realize that this, and by the way, if you write the word super defective here, I'll be very happy with that. Once we realize that it's super defective, we have to get ready to do the W's. And so for the W's, the first thing I always like to do is draw my diagram for the W's, because that kind of guides me on how I'm going to go forward with this. So for the diagram, remember in the super defective case, so actually, maybe even before I draw the diagram, I just need to remind you guys, what do we do for the second and third solutions? Right, so the second solution is going to be e to the lambda t times w1 plus t times w2. And then the third solution is going to be e to the lambda t times w3 plus t times w4 plus t squared over 2 times w5. Right. And so then I like to draw the diagram so that I can. So by the way, this is something, what makes the super defective case a little bit harder for people usually is you have more of these W's that you have to figure out. Okay, I think it's easier to get the correct W's than it is in the mixed eigenvalue case, but you do have more of them to deal with. So I'm going to draw the W3, W4, W5 diagram here, guys. W3, W4, and then we go to W5, and then we hop one more time. We're going to hit 0. And let me remind you that ultimately we are going to end up using W1 to be W4 and W2 can be chosen as W5. So we'll save ourselves a little bit of extra work there if we just duplicate the W1 with W4 and then the W2 with W5. Okay, now we have to choose this W3. I want to remind you how to do that. We're going to choose a vector. So we have 8 A minus lambda I. In this case, A minus lambda I is just A plus 5I. Let me write down what that matrix is. A plus 5I is just 0, 0, 0, 1, 0, 0, 3, 3, 0. It's just this first matrix here. Please be careful. Do not use any row reduced version of the matrix. Use the actual matrix, which is this one, okay? I need to choose a W3 that is going to survive 2 powers of that matrix, because I'm hopping to the right every time I multiply by that matrix, but should not survive 3 powers of it. To really make sure you get this right, you will need to calculate 2 powers of this matrix. So this is a little tedious, but it goes pretty quickly, especially because I have a lot of zeros here. The end of a long night, that's not a bad thing to have. So if I start calculating it out, the first row is definitely going to be all zeros. The second row is 0 plus 0 plus 0, and 0 plus 0 plus 0, and 0 plus 0 plus 0. So far we got all zeros there. But when we get to the bottom row, I have a 0 plus 3 plus 0. We get a 3 in that lower left corner. And then 0 plus 0 plus 0, and then 0 plus 0 plus 0. Okay, so there's your A plus 5I squared. And one nice thing about the super defective case is that when you do cube this matrix, it will always happen. In the super defective case, it will always happen that you will get all zeros out of that matrix. Okay, so you can kind of trust that that will happen. I've said that multiple times, which means that no matter what you choose for W3, it will hop 3 times and end up at 0. The main thing is you just need to make sure it survives this matrix. Based on this matrix, what it is, does anybody have, this is the key step, and there can be more than one right answer, but we need to choose a W3 that will survive the square matrix. Yes.
1, 0, 0.
Pretty easy. Pretty easy in this case, guys, it's just 1, 0, 0. Why? Because if I put 1, 0, 0 right here, and I work it out, I will pick off the first column of this matrix, which is 0, 0, and 3. So it survives the squared matrix, but not the cubed matrix. So this is a good choice of W3. So then let's figure out if that's W3, what are the other W's, right? So W4, if you get lost here, guys, the nice thing is the diagram can bring you back. The diagram is supposed to help you center everything about what's going on. If you've chosen W3 and you want to know, well, what is my W4 supposed to be? I just look at my picture. I have to hop 1 time to the right. So that just means I take the original matrix and I put my 1, 0, 0 right next to it. And when I do that, I will pick off the first column of this matrix. It's 0, 1, 3. That's W4. Yeah. And then W5. Well, for W5, I'm going to start with 1, 0, 0, and I'm going to hop twice to the right. Well, that's just taking the squared matrix and putting 1, 0, 0 next to it. I end up getting 0, 0, 3. Can I take 0, 0, 3 and just change it to 0, 0, 1? You know, that reminds me, on the exam the other day, I forget what the vector was that came up in the W thing. I think this was it, or something like this. I saw a lot of people who then just said equals. I was trying to eat pizza. It wasn't going down very well because people were writing this. And I was like, first of all, those are not equal. These vectors are not equal. What you really meant was maybe an arrow would have been better. And people cross this one off and they put that down. And that actually is not legal. You have to live with the W's that you obtain from the process. So if I get 003 here, I have to leave it as 003. You cannot change it to anything else. So just be careful about that. There were several people that got a little bit careless on that piece of it. And that sort of thing will make your answer incorrect, unfortunately. Okay, so at this point, we are pretty good to go, guys. X2 of t. Let's get my camera over here for this. The X2 of t just becomes, I've got the formula up there, e to the negative 5t times W1. Remember, W1 is the same as W4. So that would be 013 plus t times W5, which was 003. Okay, and then X3 of t would be e to the negative 5t. And then we have to put W3, which is 100, plus t times W4, which is 013. And then plus t squared over 2 times W5, which is 003. Yeah. So this one came out pretty clean. I actually think the super defective case is easier in my mind than the mixed eigenvalue case, because the W's are usually pretty easy to choose. Remember, out of these 5 W's, you're only choosing one of them. The rest of them just follow along the diagram. So that makes it pretty easy. And so then your final answer, don't forget to write this down, guys. I don't want to have to get my pen out. The final answer should be a linear combination of these vectors. Yeah. So that would be what you'd want to put at the end.
And this example would be homogeneous, right? Because it doesn't have the plus.
Doesn't have a plus B on it. I'm not going to do a non-homogeneous one if it's 3 by 3. That the non-homogeneous one would only be 2 by 2. It's just too hard to do the calculation by hand for anything else.
So then we would only need the complementary.
Yeah, that, oh yeah, exactly. If you just called this, sorry, if you just called this x of t, that would be okay. Yeah, same thing. Yeah. All right, guys, I think I'm kind of out of juice here. Well, actually, I'm doing okay, but I think you guys should take a break from listening to me and maybe even just take a break. You know, it's 10 o'clock. Do get some rest tonight. You want to be you don't want to be making a bunch of ERO mistakes. Even if I'm not going to take off a lot of points for ERO mistakes, it's just not going to make it a fun day for you if your EROs are all wrong and the matrices are messy and stuff like that. So try to get a little bit of rest so you're ready to get those calculations solid tomorrow. But thanks for coming. I hope it was helpful. I had a really nice turnout tonight. It's really a lot of people here, so that was good to see. I am going to go downstairs. If anybody does want to chat a little bit more, I'll go down to my office and kind of hang out down there. Otherwise, I'll be in around 8 o'clock tomorrow. So, take care.